Hello there and welcome to Just About Earth, where curiosity slows down a little and the deep past is allowed to unfold at its own pace. Tonight, we are stepping into a world that was not made for comfort, not made for certainty, and certainly not made with the future of humans guaranteed. Our subject is Dinopithecus, an ancient primate with a name that sounds like it was chosen by someone trying to win an argument in Latin. It means something close to terrible ape, which is dramatic, slightly misleading, and honestly not bad branding for a creature that may have been one of the most intimidating animals our ancient relatives ever had to live beside. Not a dragon, not a saber-tooth, not some oversized movie monster, but a giant baboon-like primate with teeth, strength, speed, and the kind of daily confidence that comes from belonging completely to a dangerous landscape. And before we settle into that old African world, let me ask you something simple and fitting for an evening like this. Where are you listening from right now, and what time is it in your corner of the world? A quiet hour, I hope, the sort that leaves room for old bones, old fears, and the very long story of how close survival can be. If this kind of slow journey into science and prehistory is your sort of thing, do give the video a like, maybe subscribe, and share this peaceful corner with someone else who enjoys learning about ancient life without being shouted at by dramatic background music every 17 seconds. I always think the distant past is unsettling enough on its own. It really does not need extra help from a drum beat. Now, with that said, there is something important to clear up right away, because the title makes a claim that sounds bold, and in a way it is meant to. Dinopithecus did not nearly wipe out humans in the neat cinematic way a title might suggest. There is no evidence for a single showdown, no fossil courtroom where we can point to one skull and say, "Ah yes, here is the exact villain of the story." What we do have is something more interesting and more realistic. We have an early human world full of hazards, tiny populations, ecological pressure, competition, predation, and constant risk. In that world, one large, highly capable, socially complex, powerfully built primate could matter a great deal. It could matter not because it was plotting against us, but because our ancestors were never far from the edge. When a lineage is small, exposed, and still learning how to survive on open ground, almost anything dangerous can become historically significant. That is why Dinopithecus deserves a careful introduction. Despite the name, it was not an ape in the modern zoological sense. It belonged to the monkey side of the primate family tree, among the hominins, the group that includes baboons and their relatives. The species most researchers recognise is Dinopithecus ingens, first named by Robert Broom in 1937, and the fossils linked to it are known mainly from South African cave deposits associated with the early Pleistocene. The picture is not perfectly tidy, because fossil primate taxonomy often behaves like a filing cabinet that was dropped down the stairs, and some material once assigned to Dinopithecus has later been reassessed or moved. Even so, the broad outline is solid enough. This was a very large baboon-like primate living in South Africa during a time when several monkey lineages, large predators, and early hominins shared the same wider region. That matters because it places Dinopithecus not in some isolated animal story, but in the same general world as our own relatives. Already you can feel the shape of the problem. When most people imagine dangerous animals in human evolution, they jump straight to lions, hyenas, leopards, crocodiles, maybe giant eagles if they are feeling adventurous. Those all deserve their reputation. But primates can be dangerous in a very different way. They are intelligent, they are social, they know how to read threat, opportunity, weakness, and advantage. Modern baboons can be bold, strategic, opportunistic, and unexpectedly aggressive. They raid crops, intimidate rivals, steal food, mob predators, and navigate complicated social lives with a level of practical competence that makes them hard to dismiss as just background wildlife. Scale that up, place it in the early Pleistocene, and imagine such an animal in a landscape where juvenile hominins were vulnerable, resources were contested, and every day required judgment about when to forage, when to move, and when to avoid a fight. Suddenly Dinopithecus stops being an odd fossil monkey and starts looking like part of the pressure system in which human survival is being tested. The age and setting make that even more compelling. South Africa, in the Plio-Pleistocene and early Pleistocene, was home to a far richer monkey fauna than the one seen there today. Researchers reviewing southern African fossil monkeys have noted that several monkey species may have lived at the same time, some in communities that also included hominins. Broader reviews of the fossil record also suggest a period in which large terrestrial papionins, including Dinopithecus ingens and Gorgopithecus major, were part of that changing southern African scene. In other words, this was not a quiet stage with one monkey, one hominin, and a convenient spotlight. It was crowded. Ecological niches overlapped, environments shifted, and large-bodied primates were not an afterthought. They were active participants in the same living system. That does not prove direct conflict at every turn, but it makes the possibility of repeated encounters very hard to ignore. And then there is the size question, which is where Dinopithecus starts to become properly unsettling. Estimates have varied, and paleontologists are careful because fossil body mass is usually inferred rather than weighed on a very large ancient bathroom scale. Still, the recurring point across the literature is that Dinopithecus was big enough to stand out even among large papionins, and likely larger than the largest living baboons. Some of the older estimates were especially dramatic, while later work has revised and debated the numbers, but the general picture remains one of an unusually large, robust primate, probably with significant sexual dimorphism, and with the kind of cranial and dental equipment you would prefer to admire from a distance. It was not some dainty tree monkey that happened to get fossilized with a stern expression. It was a terrestrial, heavy-set, formidable animal. Even allowing for scientific caution, large baboon relative you would not argue with is a fair summary. Now, when people hear nearly wiped out humans, their minds often go straight to hunting. Did Dinopithecus attack our ancestors? Did it kill them? Did it drive them from water sources? The honest answer is that the fossil record does not give us a clean police report. What it gives us is context. Early hominin life in South Africa was already precarious. Swartkrans and related sites preserve evidence of hominins living in landscapes shaped by carnivores, changing habitats, and difficult subsistence choices. Reviews of South African monkey communities have argued that hominins likely affected monkey behaviour and community structure, while work on hominin subsistence and carnivore interaction shows just how exposed early hominins were within broader predator-rich ecosystems. From that evidence, the most reasonable picture is not Dinopithecus launched a campaign against humans, but something more evolutionary and more severe. Our relatives lived among multiple pressures, and a powerful, intelligent, large-bodied primate could have added real danger through competition, intimidation, opportunistic aggression, resource conflict, and simple physical dominance in shared spaces. If populations are small enough, those kinds of pressures do not need to be constant to matter. They only need to be repeated. That is worth sitting with for a moment, because it changes how we tell the human story. We often like to imagine our ancestors as the promising main characters of prehistory, trudging bravely forward while evolution quietly clears its throat and arranges the set around them. The reality is less flattering. For most of our deep past, there was no guarantee that our line would win anything. We were not selected in advance. We were not protected by destiny, narrative structure, or the reassuring knowledge that museum gift shops would one day sell little plastic versions of our skulls. We were one experimental lineage among many, trying to persist in environments that had already been home to strong, adaptable animals for very long stretches of time. Dinopithecus belonged to one of those established lineages. It did not need to become human. It did not need tools, symbolic language, or plans for space telescopes. It just needed to be very good at being Dinopithecus, and in its own place and time, it appears to have been exactly that. Picture the broader scene carefully. Not a single cave, not a museum display but a living landscape. Open patches, brushy margins, wooded corridors, uneven ground, water sources that drew animals in and danger with them, herds moving through, cats watching from cover, hyenas ranging, birds calling, smaller primates alert to movement, hominins travelling in uncertain numbers, carrying whatever knowledge and habit their bodies and social ties could support. Somewhere in that same world, a troop of large papionins is already awake, already scanning, already deciding where to feed, where to push, where to retreat, where to dominate. Modern baboons can be noisy, forceful, and difficult to dislodge. A larger extinct relative in a harsher setting would not have needed to act like a horror creature to become a serious problem. It would only need to arrive first at the right place, hold its ground, and remind smaller, less imposing hominins that the day's plan had just changed. There is also something psychologically interesting here. We are used to measuring threat by carnivory. Sharp-toothed cat equals danger. But primate threat is more complicated because it sits uncomfortably close to us. A large cat is alien enough that the fear is simple. A giant baboon-like primate is different. It moves in ways we recognize. It has eyes that assess. It uses hands. It understands social space. It can posture, bluff, charge, coordinate, and test boundaries. That sort of threat does not just injure the body. It reshapes behavior. It teaches caution around feeding sites, around sleeping places, around exposed juveniles, around any moment of weakness. If early hominins had to repeatedly negotiate space with powerful papionins, the effect may have been broader than a rare attack. It may have changed routes, timing, vigilance, group cohesion, and access to food. Prehistory is often made of those accumulations rather than headline events, and this is where the phrase, nearly wiped out humans, starts to make more sense, provided we use it responsibly. Not as literal proof of a near extinction caused by one monkey species alone, but as a reminder that early human survival was thin enough for many pressures to matter. Climate fluctuation mattered, predators mattered, competition mattered, disease mattered, infant vulnerability mattered, access to calories mattered. A dangerous primate neighbour could fit into that list very comfortably. A lineage does not need a single catastrophic enemy to disappear. It can be worn down by the ordinary mathematics of danger. Lose a few more juveniles than you can spare. Abandon a few too many rich feeding areas. Waste a little too much energy on avoidance. Arrive late to opportunities because something stronger claimed the ground first. Do that over generations and evolutionary history begins to tilt. At the same time, I do not want to flatten Dinopithecus into a convenient monster. Fossil animals deserve better than that. Dinopithecus was not evil. It was not waiting in a cave with malicious intent and a human-centered worldview. It was an animal fitted to its environment, the product of millions of years of primate evolution. If it was imposing, that was because imposing worked. If it was large, that size meant something in its ecology. If it occupied the same general landscapes as hominins, then both lineages were navigating the same environmental realities, just with different bodies and different solutions. One of the quieter lessons of paleoanthropology is that our ancestors did not grow up in a world arranged for them. They entered communities already full of specialists, opportunists, generalists, scavengers, grazers, browsers, climbers, ambush hunters, and fellow primates with their own claims on the land. Dinopithecus reminds us that other primates belonged on that list with some force. There is another detail I like here because it keeps the story honest. Dinopithecus itself did not last. However successful it was in its time, it too vanished. That tells us something important about the world we are entering. This was not a stable paradise where the strongest simply remained forever. It was a system under pressure, changing through climate shifts, habitat restructuring, faunal turnover, and long sequences of local advantage and loss. To understand Dinopithecus properly, we cannot just stare at its size and imagine brute strength as the whole answer. We have to ask what kind of Africa could produce such an animal. support it for a time, place it in the company of hominins, and then eventually erase it. The world that made Dinopithecus was larger than Dinopithecus. It was dynamic, demanding, and full of living experiments. So, as we move forward, that is the frame I want to keep around the story. Not a campfire tale about one beast chasing one tribe, not a cartoon battle between ape and man. What we are looking at is a primate-rich, predator-rich, changing African landscape in which the human line was still fragile enough that neighbouring species could shape its chances in ways both obvious and subtle. Dinopithecus may not have come close to ending humanity in the dramatic sense of a final showdown, but it belonged to the kind of world that absolutely could have ended us. That, in some ways, is more sobering. The danger was structural. It was built into daily life. And if we want to understand why a giant baboon-like primate belongs in this story at all, then the next step is not to zoom closer to its teeth just yet, but to widen the lens and look at the continent around it. Because before you can understand the animal, you have to understand the ground it walked on. Before Dinopithecus itself comes fully into view, it helps to stop for a while and look at the continent around it, because the old South African world was not just a backdrop with a few convenient animals placed here and there. It was crowded, uneven, and already very busy long before our lineage could claim any special importance. The deposits in South Africa's cradle of humankind, which remain one of the richest sources of hominin fossils anywhere, mostly date to roughly between 3 and 1.4 million years ago. And when researchers review the animal communities from those cave systems, they repeatedly find a broad regional pattern of wooded landscapes giving way, over time and in pulses, to more grassland-dominated settings. That does not mean the whole place turned into one endless plain. It means the land was changing, and it was changing in ways that mattered to every creature trying to feed, move, hide, or raise young in it. That older Africa was also more complicated than the simple picture many of us carry around in our heads. The one where human evolution happens on a flat golden savanna, under one determined acacia tree while a lion waits politely in the distance for its cue. A better description is habitat heterogeneity. Reviews of early hominin paleo environments emphasise that these landscapes were often mixed and patchy, with different kinds of vegetation, and often with reliable water sources shaping where animals could gather and survive. South African site reconstructions point in the same direction. At Kromdraai, the fauna has been interpreted as suggesting a mosaic woodland savanna, while other cradle sites preserve evidence for combinations of grassland, woodland, bushland, rocky ground and water-adjacent habitats. So when we imagine the setting, it is wiser to think in pieces: grassy stretches, brushy cover, riverine zones, wooded pockets, stony rises, and caves opening into a living map of opportunity and risk. That mattered because mixed ground creates mixed traffic. Water attracts herbivores. Herbivores attract carnivores. Trees offer safety to some animals, ambush cover to others, and vantage points to anything clever enough to use them properly. Open patches reward speed and vigilance but punish hesitation. Rocky hills break sight lines. River edges bring shade, food, and the possibility that something with teeth arrived before you did. At Swartkrans, for example, reconstructions have described a wooded grassland with rocky hills and riverine woodland savanna, with fauna that suggests nearby water, as well as a generally more open setting than some earlier South African cave deposits. In plain terms, this was not a calm, balanced postcard. It was a landscape in which conditions could change over a short distance, and where being in the wrong patch at the wrong moment could be the sort of mistake one only makes once. And the animals using that terrain were not modest little placeholders waiting to be introduced properly later. Southern Africa, in the late Pliocene and early Pleistocene, was home to large mammal communities that were themselves shifting through time. One study of these faunas identified at least 3 major large mammal associations between 4.5 and 0.5 million years ago, with a substantial turnover between 3.0 and 2.0 million years ago, and another notable change around 2.61 to 2.4 million years ago. That is the sort of information that sounds technical until you realise what it means on the ground. Whole communities were being reorganised. Species were appearing, disappearing, moving, adapting, or failing to adapt. The ecological rules were not fixed. For any small, vulnerable, slowly reproducing lineage, including our own relatives, that is not a comfortable way to live. In such a world, size still counted for a great deal, and Africa had no shortage of animals built on a scale that would have made any early hominin think twice. The cave faunas of the cradle include elephants, large bovids, equids, suids, hippos in the broader regional record, and a deep roster of carnivores and primates. Even when paleo-environmental interpretations differ from site to site, the overall impression is one of a continent where large-bodied mammals were not occasional spectacles but regular features of everyday life. It is easy for modern people, who mostly encounter wild animals through screens, fences, or the reassuring distance of zoom lenses, to underestimate what it means to live among heavy, confident creatures that do not care at all whether you have plans for the afternoon. Early hominins were not visiting wilderness. They were living inside it. The predators alone deserve a moment of quiet attention. Swartkrans has yielded or been associated with a carnivore guild that included extinct cats and hyenas, formidable enough to make the place feel less like a nursery of human evolution and more like a long argument about who got to leave the cave alive. Summaries of the site mention large carnivores such as Dinopithecus, Meganterion, Macarodus, Homotherium, Chasmoporthetes, and Pachycracuta as possible contributors to the risks faced by the animals there, including hominins. Drimolen and other nearby localities also preserve evidence of saber-toothed cats, hyenids, canids, and other carnivores. This is an important corrective to the tidy version of prehistory in which our ancestors walked confidently from one innovation to the next. Much of the time, they were sharing the landscape with animals that could overpower them very efficiently. There is also evidence that our relatives were not merely theoretical prey in some abstract food web diagram. South African research on hominin behaviour has repeatedly taken predator pressure seriously, and commentary on possible predator avoidance has used living baboons as one useful comparison, because baboons and australopiths are broadly similar in body size, terrestrial habits, and vulnerability to large carnivores. Modern baboons cope by living in groups, using vigilance, moving in patterned ways across the landscape, sleeping in inaccessible places, and sometimes associating with other species in open country, where senses can be combined for mutual warning. None of that proves early hominins copied baboons point for point, but it does remind us that medium-sized primates on dangerous ground do not get to be careless. They survive by being alert, social, and difficult to surprise. Once you understand that, the phrase "Africa still belonged to giants" stops sounding like exaggeration and starts sounding like an ecological summary. The continent did not belong to humans yet, if "belong" is even the right word. It belonged to whichever animals were best fitted to particular corners of a changing landscape. Some were huge herbivores, some were specialised carnivores, some were monkeys, some were hominins, but only in the limited sense that our relatives had found a way to persist there, not in the triumphant sense of having mastered it. Even the cave sites that now feel intimate to us because they preserve hominin bones were once simply pieces of terrain being used, contested, and interpreted by many species at once. A cave mouth could be shelter, trap, lookout, den, feeding station, or death site, depending on who reached it first and who was waiting nearby. This is also where the primates become especially interesting, because Africa was not just full of impressive mammals in general, it was full of impressive primates. The southern African monkey fauna of the Plio-Pleistocene was more diverse than the one seen there today, and researchers have argued that at or shortly after about 1.75 million years ago, there was a radiation of large terrestrial papionins, including Dinopithecus ingens and Gorgopithecus major. Other work on baboon evolution notes that several large-bodied monkey taxa, were contemporaneous and possibly sympatric with early Pleistocene Papio fossils in southern Africa. That is a wonderfully scientific way of saying the place may have had several substantial baboon-like primates moving through the same broad world at roughly the same time. If you're a small hominin trying to judge what counts as a serious problem, that certainly qualifies. It is worth pausing here because modern people often file monkeys into the mental cabinet marked clever but not too worrying, which is a category that works fine until the monkey in question is large, terrestrial, socially organised, and entirely at home in rough country. Living baboons are already strong enough, bold enough, and opportunistic enough to complicate life for leopards, farmers, dogs, and occasionally each other in ways that suggest a clear institutional dislike of orderly boundaries. Fossil pepionins larger than modern baboons would not need any extra drama added to be ecologically significant. They would have been noticeable, noisy when they wanted to be, defensive when challenged, and perfectly capable of dominating feeding spots or intimidating anything not prepared to escalate. In a world where early hominins were still physically vulnerable, such neighbours did not have to prey on them regularly to become part of the pressure system shaping their behaviour. There is another reason the primate angle matters. Competition from a fellow primate is different from danger posed by a cat or hyena. Predators mainly force you to avoid being eaten. A large monkey can do that and more. It can compete for food. It can pressure access to water. It can harass. It can claim sleeping sites or approach routes. It can interpret signals of weakness quickly because it is, in its own way, reading the same social world. Modern baboon behaviour has long been considered useful for thinking about the problems early hominins faced in open country. And even without forcing the analogy too far, it is easy to see why. A dangerous feline is terrifying. A dangerous primate is unsettling in a different way, because its actions are less alien and often more flexible. That sort of animal can become a daily nuisance, an occasional threat, and a strategic competitor all at once, which is an impressively rude combination. Meanwhile, the hominin story in South Africa around 2 million years ago was itself far from simple. Drimolen, one of the key cave systems in the cradle, has provided evidence that around 2.04 to 1.95 million years ago, early Homo and Paranthropus robustus were present in the same broader karst landscape, while Swartkrans preserves evidence that multiple hominin species coexisted there as well. So the human line was not one tidy procession moving single file toward modernity. It was plural, overlapping, and in some cases living close enough in time and place to make the neighbourhood feel crowded, even before one adds the saber-toothed cats, hyenas, pigs, antelope, and giant monkeys. There is a tendency to imagine evolution as if every scene contains only the species most relevant to the final outcome. The fossil record keeps correcting that fantasy. Real environments are untidy. They are full of overlap, and overlap is exactly what makes the old African setting so compelling here. The same region that preserved hominin bones also preserved papionins, carnivores, ungulates, and the traces of changing conditions under which those animals lived. Researchers working across the cradle now emphasise that paleo-environmental reconstructions there often show repeated fluctuations from wetter to drier conditions, mixed evidence of open grassland and more closed wooded habitats, and, overall, a progression that can include movement toward more grassland-rich settings. That kind of instability rewards flexibility, but punishes specialisation at the wrong moment. It means that any species surviving there had to navigate not just other animals, but changing rules about food distribution, cover, visibility, and water. Giants do well in some conditions, then conditions shift. New competitors arrive. Old strategies become less reliable. The land does not stay impressed forever. That helps explain something that might otherwise seem contradictory. If Africa still belonged to giants, why did some of those giants disappear? The answer is that dominance is local and temporary. Dinopithecus vanished. So did several of the other imposing animals that once shaped these communities. Even some lineages that seem stable in the fossil record turn out, on closer inspection, to be moving through windows of opportunity rather than enjoying permanent ownership of the landscape. The old world was full of powerful animals, but it was not a static kingdom. It was an active sorting process. Species held on for a time, expanded, shifted, declined, or were replaced. Humans survived not because the system favoured us from the start, but because our ancestors stayed in that sorting process long enough for later advantages to accumulate. In the earlier phases of the story, that outcome was still very much in doubt. So when we picture this period properly, we should not see a young humanity striding confidently into its inheritance. We should see a primate lineage still learning how to remain present in a hard and unstable world. The ground underfoot alternated between wooded refuge and exposed grassland. Nearby water promised life and danger in the same package. Carnivores ranged widely, other hominins were around, large monkeys were around, community structure was shifting, climate was nudging habitats in new directions. In that setting, a giant baboon-like primate was not an odd side note. It was part of the architecture of risk. And once the wider African stage is set like that, Dinopithecus no longer feels like a dramatic title in search of a story. It feels like exactly the sort of animal that would emerge from such a place, built by it, sharpened by it, and ready to make life more difficult for anything smaller, slower, or less sure of itself. Which means the next thing to do is stop looking at the continent from a distance and finally turn toward the animal itself. Because once you place Dinopithecus inside this world, its size and design start to matter a great deal. Once you place an animal like Dinopithecus inside that older South African world, the next question becomes very simple. What exactly was it built to do? Not in the heroic sense, not in the way documentaries sometimes speak as if every extinct animal woke up each morning with a narrated destiny, but in the practical sense. What kind of body was this? What sort of feeding, moving, threatening, enduring creature does the fossil evidence suggest? And the first thing to say, before the image grows too confident, is that Dinopithecus is known mainly from craniodental material. In other words, skulls, jaws, and teeth do most of the work here. That is both helpful and limiting. Helpful, because primate skulls carry a remarkable amount of ecological information. Limiting, because when the limbs are missing, you cannot simply watch the skeleton stand up and confess its habits. A line from the latterly Cercopithecid literature says it plainly: no postcranial elements of Papio, Dinopithecus, ingens, or any other equivalently large baboon had yet been found, which means any reconstruction of posture and locomotion remains an inference rather than a full body reading. Even with that limitation, Dinopithecus does not emerge as vague. Quite the opposite. It comes into view as one of the larger and more imposing African papionins in the fossil record, and that point appears again and again across later discussions of the taxon. Current summaries generally recognise one valid species, Dinopithecus ingens, first named by Robert Broom in 1937 from material associated with the Schuurberg region, with additional South African occurrences usually including Swartkrans member 1 and fossil material historically attributed from Sterkfontein as well, though the exact provenience and taxonomic history of some older collections remain part of the usual South African cave site headache. The taxonomic mess is real enough that one of the more useful lessons from recent Papionin work is not to sound too relaxed when saying any fossil monkey name out loud. Still, Dinopithecus ingens is widely treated as a real and distinctive large-bodied form rather than just a badly behaved oversized Papio specimen. The age range helps anchor that picture. Cercopithecid-based biochronological work has constrained Dinopithecus ingens at Swartkrans to roughly 2.1 to 1.7 million years ago, placing it squarely in that early Pleistocene interval, when southern African primate communities were diverse, hominin sites were active, and environmental conditions were shifting in ways that affected who could hold ground and who could not. That may sound like a simple date range, but it matters because it tells us Dinopithecus was not some ancient oddity from a separate era. It belonged to the same broad ecological world that housed early Homo, Paranthropus robustus, large carnivores, and multiple monkey lineages. It was part of the active present of those landscapes, not a ghost from some comfortably earlier time. Now, if you want the shortest responsible description of its skull, one good scholarly summary gives exactly the right tone. Dinopithecus ingens is distinguished from other papionins by a robust and rugged skull, with a strong masticatory apparatus, a long muzzle, and a broad interorbital region. That phrase does quite a lot of work. Robust and rugged suggests the overall impression of the cranium is not graceful or lightly built. Strong masticatory apparatus points to the muscles and skeletal architecture involved in biting and chewing. A long muzzle places it in familiar baboon-like territory, rather than the shorter face condition seen in some other monkeys, and a broad interorbital region means the area between the eye sockets was relatively wide, contributing to a face that likely looked powerful even before one gets to the canines. In short, the head was built like a serious piece of equipment. That matters because in papionins the skull is not just a container for the brain and a bracket for the teeth. It is part of the social and ecological toolkit. The muzzle houses the canines, the jaw system handles a broad range of foods, the facial structure bears the signatures of size, sex differences, and often dominance-related display, and the overall cranial shape can reflect both phylogeny and function. Dinopithecus appears to have shared numerous craniodental similarities with modern baboons, which is one reason some earlier researchers treated it as a subgenus of Papio rather than a fully separate genus. More recent cladistic work has been less inclined to collapse everything into Papio, but it still places Dinopithecus among crown African papionins and treats it as a close part of the same broad evolutionary conversation rather than an isolated experiment. So when we imagine it, the safest route is not to invent something wildly unfamiliar. It is to start with baboon logic and then increase the mass, the ruggedness, and the intimidation factor. Size, of course, is where Dinopithecus gets its reputation, and here some caution is useful. Older popular descriptions sometimes inflate fossil primates with great enthusiasm, as though the only two available categories were reasonably large and nightmare fuel. The more scholarly point is steadier. Dinopithecus was a very large papionin, larger than the largest living baboons in many reconstructions, but exact body mass estimates vary depending on which teeth are used, which comparative samples are chosen, and how much confidence one is willing to place in allometric scaling from limited craniodental remains. Comparative work on South African fossil monkey cranial variation also makes clear that allometry is everywhere in this material, meaning size strongly shapes form and can complicate taxonomic interpretation if one is not careful. So the safest way to say it is not with a dramatic exact number, but with a functional conclusion. This was a very large baboon-like primate, large enough that body size itself was one of its defining traits. And large size in a terrestrial primate is not a decorative feature. It changes almost everything. It affects who can threaten you, who you can threaten, which foods are worth the effort, how far you can travel, how much heat you carry, how much water and energy you need, and how much social friction your body can back up in a confrontation. In primates, especially in the papionin world, size also interacts with sexual dimorphism, and Dinopithecus is explicitly described in the literature as a very large and sexually dimorphic fossil baboon species. That phrase deserves a slower reading. Sexual dimorphism means males and females were likely different in size, and perhaps in the extent of some cranial features, which in living papionins often ties closely to social competition, display, and hierarchy. A large dimorphic papionin is not usually a quiet little forest browser minding its own business in complete egalitarian harmony. It is the sort of animal that may have lived in a social system where size, rank, and male competition mattered quite a lot. You can almost reconstruct the general impression from that alone. A big male Dinopithecus would likely have presented the combination that modern baboons already do so well, only with more scale behind it. Forward-projecting muzzle, substantial canine display, heavy jaw musculature, and the confidence of an animal whose face was both a feeding apparatus and a warning sign. Modern baboons do not have to bite very often for their mouths to be persuasive. Much of the work is done in posture, charge behaviour, and open-jawed threat. Dinopithecus, if built along similar lines but with greater mass, would have carried that same kind of authority in amplified form. It may not have needed to be especially fast by the standards of lighter primates if it could dominate by presence, group coordination, and a willingness to escalate. The most unsettling animals are not always the ones that must attack. Sometimes they are simply the ones everybody else already knows to avoid. That is a kind of power too, and in a crowded early Pleistocene landscape it may have mattered more than cinematic aggression ever would. The fossil record does not show us a troop in motion, but the anatomy invites a very particular kind of inference. Then there is the issue of locomotion, which is one of those areas where science is honest enough to be slightly frustrating. Because no securely attributed postcranial material is generally recognised for Dinopithecus, no one can say with full anatomical confidence exactly how its limbs were proportioned, or how much time it spent in trees versus on the ground. Still, Papillonian identity and large size are not meaningless clues. Scholarly summaries routinely infer that an animal like this probably spent significant time on the ground and moved quadrupedally. That is a reasonable inference, not a fantasy. Large-body papillonins tend toward terrestriality, and the ecological setting of the South African cave faunas also makes a terrestrial component entirely plausible. In other words, while we should avoid pretending to know the exact spring of its stride, it would be stranger if Dinopithecus had been an especially arboreal specialist than if it had been a mostly ground-using, baboon-like quadruped that could still exploit elevated refuge when needed. Diet adds another important layer, because power is not only about fighting, it is also about flexibility. A large primate that can only survive on one narrow class of food is impressive right up until that food becomes scarce. Dinopithecus appears to have avoided that trap. Isotopic work on South African Plio-Pleistocene baboons found that Dinopithecus did use savanna-based C4 resources, and in fact more than some earlier expectations had predicted, though it was nowhere near as grass-focused as Theropithecus oswaldi. Dental microwear studies have also suggested a broad and eclectic feeding pattern, with one common comparison being to the living yellow baboon. That is an important comparison because yellow baboons are not delicate specialists. They are generalist feeders capable of taking fruit, seeds, underground resources, invertebrates, and occasional animal matter depending on habitat and opportunity. Dinopithecus, then, was likely not built for one dietary trick. It seems better understood as a large, adaptable consumer with a mixed strategy. That mixed strategy becomes even more interesting when set beside older morphological predictions. Some studies based on molar adaptations had suggested a diet with a high proportion of fruit and relatively fewer leaves, while isotopic evidence later indicated more use of savanna-linked resources than expected. Those findings are not necessarily contradictory. A generalist primate can prefer certain foods when conditions are good, and widen its menu when conditions are harder, or when local habitats make different resources profitable. In practical terms, that means Dinopithecus may have had one of the most useful ecological qualities an early Pleistocene animal could possess: room to adjust. It could exploit C3 foods associated with woody vegetation, but it was not trapped there. It could make use of open country resources without becoming the sort of highly specialised grazer represented by Theropithecus. That sort of dietary breadth does not just help a species survive. It also makes it a more capable competitor, because broad feeders can follow opportunity instead of waiting politely for one plant community to cooperate. And that returns us to the chewing apparatus. A strong masticatory system in a papillonin is not simply about brute force for its own sake. It is about handling a wide mechanical range of foods across seasons and patches of habitat. Hard objects, tough items, fibrous fallback foods, fruits when available, perhaps below-ground resources or abrasive foods contaminated by grit, all place different demands on the teeth and jaws. Dinopithecus seems to have combined a large body with a skull equipped to process varied resources efficiently, which is precisely the kind of design one expects in a powerful terrestrial generalist. There is a tendency in popular writing to treat teeth as if they only tell us who bit whom, but far more often they tell us who could keep eating when conditions worsened. In evolutionary terms, that is the more serious advantage. A lineage can survive many dramatic moments if it wins the slow contest of bad seasons. Dinopithecus looks like an animal designed to do that reasonably well. The social side of power is harder to prove directly, but it would be strange to ignore it. Papionins are social primates, and many features of their lives, from vigilance to movement to defense against predators, only make full sense in groups. We cannot excavate a troop formation out of breccia, but the broader behavioural model is still useful. A large-bodied, sexually dimorphic terrestrial papionin likely did not operate as a lonely wanderer drifting romantically across the veld in search of meaning. It likely lived in some kind of socially structured setting where rank, mating competition, coalition behaviour, alarm and group movement mattered. That matters because a big primate is one thing. Several big primates who understand each other's signals are another. The difference between a single dangerous animal and a dangerous social system is enormous. It changes how water sources are approached, how carcasses are contested, how juveniles are protected, and how much risk a smaller neighbour must accept simply to continue using shared ground. This is also the point where Dinopithecus becomes more unsettling than a mere size comparison. If all it had been was large, it would still be interesting. But what the evidence hints at is a combination of traits that travel well together in difficult environments. Substantial body size, a tough skull, a flexible diet, probable terrestrial competence, and likely social complexity. That is not the profile of a clumsy giant. It is the profile of an animal that could hold its own. When we talk about something being built for power, that is what we mean in evolutionary terms. Not maximum violence, not maximum myth. Maximum practical effectiveness in the kinds of situations that decide whether a lineage keeps going. Dinopithecus does not have to be imagined dragging hominins around like a villain in a very overfunded museum trailer to matter. It only has to be imagined arriving at contested places with enough physical and social weight that others had to make room. There is one more subtle point worth keeping in mind. Comparative analyses of fossil South African papionins show how strongly skull measurements can be shaped by size itself, which means some of the apparent distinctions among fossil monkey taxa must always be interpreted carefully. Yet Dinopithecus keeps returning as a recognisable large-bodied form within that complicated record. In other words, even after later researchers tried to clean up the old taxonomic cupboard, Dinopithecus did not simply dissolve into nothing. That persistence matters. It suggests there really was something distinctive in the Southern African record, not just an ordinary baboon puffed up by wishful thinking, or a few oversized teeth giving paleontologists an exciting afternoon. The animal may remain incomplete, but it is not imaginary. So the picture that emerges is not perfect, but it is strong enough to feel real. Dinopithecus was a very large, sexually dimorphic, baboon-like monkey of the early Pleistocene South African world, known mainly from skulls and teeth, with a robust face, heavy chewing apparatus, long muzzle, broad interorbital region, likely terrestrial habits, and a flexible feeding strategy that drew from more than one part of the landscape. That is already enough to understand why it would have been imposing. It is also enough to see why early hominins, who were themselves living as vulnerable primates in the same general ecosystems, would not have encountered such a creature as decorative wildlife. They would have encountered it as another claimant, another intelligence on the land, another body with its own appetite and priorities. And once you have an animal like that clearly in mind, the next question is no longer what Dinopithecus was built to do. The next question is what sort of trouble an early human world could expect when a primate built like that was already there. Before a creature like Dinopithecus becomes a threat in the story, the human side of the landscape has to come into focus, because it is very easy to imagine our early relatives as tougher, safer, and more in control than they really were. When we look at the South African record around 2 million years ago, what we actually see is not a confident species steadily marching towards success, but several hominin forms trying to persist in a region that was changing fast. At Drimolen Main Quarry, fossils show that Paranthropus robustus and an early Homo with affinities to Homo erectus were present between about 2.04 and 1.95 million years ago, and the broader South African record suggests a period of unusually high hominin diversity around 2.1 to 1.9 million years ago. That means these landscapes were not hosting one clear human winner. They were hosting overlap, experimentation, and competition under shifting ecological conditions. Those shifting conditions mattered just as much as anatomy. The South African karst region northeast of Johannesburg was not one stable habitat but a patchwork of wooded areas, grassier stretches, rocky ground and riverine zones, with a wider trend across cradle sites showing wooded landscapes giving way over time to more grassland-rich settings. For Swartkrans specifically, faunal reconstructions have described a wooded grassland with rocky hills and riverine woodland savanna, while other evidence suggests increasingly open conditions were becoming important in the region. That kind of landscape rewards flexibility, but it also creates exposure. A hominin moving from wooded cover into open ground gains visibility for spotting danger, but also becomes more visible to anything already watching. A route to water may also be a route to predators, rival primates, and larger animals with no particular interest in sharing. Climate was pushing this whole system harder than any single species could control. Work at Drimolen argues that between about 2.3 and 2.0 million years ago, southern Africa was going through major ecological change, with increasing aridity and climate variability after about 2.2 million years, broader faunal turnover, local extinctions, incoming species, and new radiations. In plain terms, the rules of the neighbourhood were being rewritten. Food distributions changed, habitat boundaries shifted, and older lineages that had done well under previous conditions no longer had guaranteed security. This is one reason it makes sense to talk about early humans as living in a dangerous landscape, rather than simply a predator-filled one. Predators were part of the danger, certainly, but so were instability, competition, and the constant need to make good decisions in an environment that did not stay still long enough to become forgiving. It is also worth noticing that the first humans in this setting were not physically imposing by the standards of the fauna around them. South African researchers have often used baboons as a behavioural comparison for extinct hominins, because baboons are broadly comparable in size and weight to australopiths such as Paranthropus robustus and Australopithecus africanus, and because both are terrestrial primates navigating exposed ground in predator-rich environments. That is not meant to diminish our relatives, it is meant to put them in the correct scale bracket. They were not giant hunters towering over the ecosystem, they were medium-sized primates in a country of large carnivores, large herbivores, and large monkeys. A recent 2025 study from Swartkrans sharpened that picture further by describing an articulated Paranthropus robustus, hip, femur, and tibia from member 1, and concluding that the individual was one of the smallest known adult hominins in the fossil record. The old human world was not filled only with sturdy, broad-shouldered prototypes of us. Some of these individuals were small enough to look very vulnerable indeed. That vulnerability was not hypothetical. Swartkrans has long been one of the key places where the old romantic picture of humans as natural-born top predators started to come apart. The famous specimen SK54, recovered from the member one-hanging remnant deposits dated around 1.9 to 1.8 million years ago, preserves puncture marks that strongly indicate leopard predation. A 2024 reassessment argued that SK54 is more likely Homo than Paranthropus, which matters because it weakens the older habit of treating early Homo as the technologically superior predator, while placing Paranthropus in the role of prey. At least in this case, Homo itself may have been on the menu. That is a bracing correction. It means that even the lineage we like to cast as the clever one was not walking through South Africa under some protective glow of inevitable success. Swartkrans tells a broader version of the same story. The site has yielded rich hominin, faunal, and artifact accumulations, and it was once proposed that hominins only really began using the cave more safely after gaining control of fire in Member 3, a supposed shift in the balance of power. But later work identified butchered bones in all 3 major units, rather than only in Member 3, complicating that neat scenario. In other words, early hominins were already processing animal remains at Swartkrans before any simple story of fire-secured cave occupation can be accepted. They were finding meat, accessing carcasses, and doing useful work with tools in a place that still remained heavily entangled with predators. That makes their lives more impressive, but not necessarily safer. It suggests persistence under danger rather than mastery over it. The stone tools themselves help us picture that persistence. Newly described material from the lower bank of Swartkrans. Member 1 has been confidently assigned to the older one, and burial dating established an age of about 2.22 plus or minus 0.09 million years for a large portion of that lower bank, making it the oldest occurrence of older one stone tools and Paranthropus robustus in South Africa. This is important because it places tool use right inside the dangerous landscape rather than after it. Early humans were not passive creatures waiting for a later technological miracle. They already had flake stone, already knew how to cut, already had some ability to exploit carcasses and reshape opportunity. But older one tools do not turn a small primate into a lion. They help with access, processing, defense in some contexts, and perhaps confidence at a carcass. But they do not erase speed disadvantages, climbing disadvantages, or the risk of being surprised by something stronger. This is where it helps to think about daily life, rather than grand milestones. Imagine a small group of hominins leaving a sleeping place at first light. They need food, water, and social cohesion before anything else goes wrong. They also need to avoid being isolated. A lone individual is easier to target, easier to intimidate, and less able to monitor multiple directions at once. Work on predator avoidance in South Africa has suggested that behavioural analogies from living baboons may be useful here, precisely because medium-sized terrestrial primates survive through vigilance, grouping, strategic use of habitat, and careful reading of the landscape. That does not mean our relatives behaved exactly like baboons. It means they lived under the same unforgiving arithmetic. Eyes matter, numbers matter, access to cover matters, timing matters, knowing where the dangerous places are matters, and knowing that danger changes with season, light, and the movements of other animals matters even more. The dangerous places, naturally, were often the useful places. Water drew life in, and with it came risk. Rocky slopes could provide shelter and lookout points, but also ambush cover. Open areas could offer tubers, scattered carcass remains, or paths of movement for herd animals, but also forced hominins into view. Caves might function as shelters or repeated use places, but they were also part of carnivore landscapes, not private homes with a lock on the door. South African cave taphonomy has been shaped for decades by the recognition that carnivores contributed heavily to these bone accumulations, and later work on Swartkrans Member 3 showed abundant tooth marks and evidence that multiple carnivore taxa, not just leopards, helped form the assemblage. So even the places that now preserve human storylines were once shared spaces with very poor property rules. One can almost hear the ancient legal dispute now. Yes, the cave contains tools, but unfortunately it also contains cats. There is another pressure that matters here, and it tends to be underestimated because it sounds less dramatic than predation. Competition with other hominins and with other intelligent, opportunistic animals could quietly shape survival every bit as much as direct attacks. At around 2 million years ago, South Africa preserves evidence that Australopithecus, Paranthropus, and early Homo all overlapped regionally within the same broadcast landscape, even if strict site-by-site symmetry cannot always be demonstrated. Add to that the presence of large papionins and a changing mammal community, and the result is not just danger from being eaten, It is danger from being outcompeted, displaced, or forced into less favourable parts of the habitat. A small hominin group that reaches a food patch second, loses a route to water, or gets pressured away from a safer sleeping area does not need a dramatic fight for the consequences to become serious. Evolutionary losses are often cumulative long before they are spectacular. At the same time, the first humans in this landscape were not helpless. That is the part that can get lost if we lean too hard into danger. They endured. They used stone. They processed animal tissue. They moved through mixed terrain. They likely shared information, protected juveniles as best they could, and developed habits that made repeated survival possible. The fact that Homo and Paranthropus persisted through these conditions at all tells us they were behaviourally capable animals, not just nervous passengers in a predator reserve. The correction is not that they were weak. The correction is that they were contested. Their abilities were real, but so were the limits of those abilities. A stone flake can open marrow-rich bone or strip meat from a carcass, but it cannot guarantee that the owner of the carcass will not return. A group can improve vigilance, but it cannot keep every child safe forever. Intelligence helps, but it does not stop drought, habitat turnover, or a leopard descending at speed from exactly the wrong branch. This is also why the old human habit of treating technology as an instant victory is misleading. We like beginnings that look like breakthroughs. The first tools, the first fire, the first proper hunter, the first species that feels enough like us to make the rest of the landscape look outdated. But South Africa around 2 million years ago does not really cooperate with that story. It gives us tool makers who are still prey. It gives us multiple hominin lineages rather than one clear successor. It gives us caves that preserve both human activity and predator power. It gives us environmental change severe enough to restructure faunas and perhaps push some lineages to extinction. That is a harder story, but a better one. It treats early humans as animals first, clever, adaptable, social, but still subject to the same ecological rules as everything else alive around them. Once you accept that, Dinopithecus starts to fit into the scene much more naturally. A dangerous landscape is not made dangerous by one villain alone. It is made dangerous by layers, climate instability, patchy habitats, large carnivores, uncertain shelter, overlapping hominin species, and other primates that were already strong, social, and well adapted to the same ground. The first humans did not step into an empty future. They stepped into a crowded present. Some days they would have found food and moved well and stayed together. Other days they would have arrived late, been watched, backed off, or lost. That is the kind of landscape that teaches hard lessons fast. And if we want to understand why a giant baboon-like primate could matter so much in such a world, then the next thing to examine is not simply that it was large, but the rules that size, teeth, force, and nerve imposed on everyone living nearby. By the time a landscape has taught its inhabitants how to stay alive, it has also taught them what matters most. And in the early Pleistocene, that lesson was not subtle. Teeth mattered, body size mattered, nerve mattered, group size mattered. The ability to read danger before danger fully arrived mattered perhaps most of all. In primates, canines are not just leftovers from some ancient design scheme or decorative bits of dental architecture placed there for a dramatic smile. In many species, they function primarily as weapons in conflict, especially conflict among males, and a study of wild male yellow baboons found that, after controlling for age, longer canines were associated with higher adult dominance rank. That does not mean every disagreement ended in blood. It means the mouth itself formed part of the social order. When a primate opens its jaws and shows what it can do, that display is carrying real information about fighting ability, status, and consequence. In a world where injuries are expensive and weakness can be quickly exploited, a threatening face can be as important as a strong bite. That is one reason Dinopithecus deserves to be taken seriously. It was not merely another monkey in the South African fossil record, but a very large and sexually dimorphic fossil baboon species, distinguished by a robust and rugged skull, a strong masticatory apparatus, a long muzzle, and a broad interorbital region. Those details may sound technical, but together they describe a head built for work and for warning. A long muzzle means room for large canines. A strong chewing system implies substantial musculature, and a skull able to tolerate force. Sexual dimorphism suggests males and females likely differed enough in size and perhaps facial development that male-male competition was probably important in the species' life history. In practical terms, Dinopithecus looks less like a shy general-purpose monkey and more like the sort of primate that could dominate through a combination of sheer build, social pressure, and the universal persuasive power of a face full of sharp teeth. Modern baboons help make that more concrete, because they show how much of primate survival and primate power is negotiated before any full fight begins. In wild baboons, male-male contests over dominance, rank, or access to females may involve canine displays and bites, and the injuries from those bites can occasionally be lethal. The same Ambercelli study that linked longer canines to higher rank also notes that high-ranking male baboons are more likely to gain mating opportunities and sire offspring. So the teeth are not just for eating and not just for emergencies, they are built into the social economy. They shape who advances, who backs down, who is challenged, and who is not worth testing. If Dinopithecus operated in a similarly structured social world, and there is no obvious reason to imagine it was exempt from Papianin logic, then its teeth were part of a much larger system of authority. They would have affected feeding order, male rivalry, troop defence, and probably how other animals, including hominins, judged the cost of standing their ground. The chewing apparatus matters for another reason too, and it is a quieter one. Survival is not only decided by fights, it is decided by who can keep eating when conditions worsen. Dinopithecus appears to have had more dietary flexibility than earlier expectations suggested. Stable isotope work on South African fossil baboons found that Papio, Dinopithecus, ingens used more savanna-based C4 resources than previously predicted, with some individuals apparently getting roughly 10% to 30% of their diet from C4 material. That does not make it a grass specialist like Therapithecus, but it does suggest ecological breadth. A large-body primate able to draw food from more than one part of the landscape is harder to starve out and harder to displace. It can track opportunity. It can use wooded and more open settings without being fully locked into one. In a variable environment, that sort of flexibility is a form of strength every bit as real as biting power. A creature that can threaten and endure at the same time becomes a more serious neighbour than one that can only do one of those things well. And then there is the group itself, because no medium-sized terrestrial primate survives long in dangerous country by acting alone. Research on modern baboons used as analogues for early hominin anti-predator behaviour emphasises just how many strategies are built around collective defence. Baboons live in large troops, move in patterned ways across the landscape, use sentries, sleep in inaccessible places at night, throw stones in some contexts, and often associate during the day with other species such as impala, whose senses complement their own. That is a useful reminder that survival in open and mixed habitats is rarely a matter of individual courage. It is a matter of systems, many eyes, good timing, clear alarm signals, safe sleeping places, and the discipline to move together when danger is sensed. These are not luxuries. They are what stand between a primate troop and becoming a repeated food source for larger carnivores. Even so, none of those defences create safety in any absolute sense. A study of olive baboons and leopards notes that baboons regularly sleep on cliff faces and in trees at night, apparently to reduce predation risk, yet they are most often killed by leopards at or near those sleeping sites. That detail is almost rude in its efficiency. It means the safest place may still be dangerous. It is simply less dangerous than the alternatives. The same broader lesson comes through the South African hominin record. The reassessment of the iconic Swartkrans cranium, SK54, argues that the fossil is best attributed to Homo rather than Paranthropus, and emphasises that Homo was also prey for leopards in the early Pleistocene. So when we talk about the rules of survival, we are not describing how to become secure, we are describing how to improve the odds just enough to remain present in the landscape. The system does not reward perfection. It rewards those who lose a little more slowly than their competitors and predators expect. That is where strength has to be understood correctly. It is tempting to hear strength and think only of muscles, but in a primate world, strength is composite. It includes body mass, jaw power, canine size, confidence in conflict, social backing, and the ability to hold access to useful places. A big male baboon with long canines and high rank is not merely stronger because he can bite harder. He is stronger because his body and status alter the behaviour of everyone around him before contact is made. Others move aside, others hesitate, others calculate differently. Dinopithecus, with its very large size and rugged cranial design, likely carried that kind of field effect around with it. Not magic, not myth, just the practical influence of a body that makes other bodies reconsider their plans. In contested environments, power often lies in forcing others to pay the cost of avoidance, while you continue feeding, drinking, or moving through a route as if it belonged to you. Seen from that angle, the early human problem becomes easier to understand. Hominins in South Africa were not confronting a single type of threat. They had to account for leopards that could kill them at night, larger carnivores across the wider landscape, climate-driven changes in habitat, and other primates whose social and physical advantages could make daily life more difficult. The reason baboons remain such valuable analogues in discussions of early hominins is not because hominins were simply baboons with ambitions, but because both were medium-sized terrestrial primates facing some of the same ecological pressures. They had to solve comparable problems of grouping, vigilance, movement, and trade-offs between food access and predation risk. The difference is that hominins were also experimenting with tools, carcass access, and their own evolving forms of cooperation. Useful advantages, certainly, but not automatic ones. A stone flake does not cancel a leopard. It also does not persuade a large confident primate troop to surrender a feeding area out of respect for future technological progress. There is also a blunt rule here that applies across many dangerous landscapes. Juveniles magnify vulnerability. Baboons rely heavily on group-based anti-predator behaviour precisely because not every member of a troop is equally able to flee, fight, or detect trouble early. Hominin groups would have faced the same arithmetic. A group does not move at the speed of its strongest adult, but at the speed allowed by infants, children, injuries, pregnancy, fatigue, and uncertainty. This is why teeth and intimidation can matter so much even without regular killing. If a large papillon troop can pressure another primate group off a route, delay its access to water, or make it avoid a productive area at key times of day, then the costs fall unevenly on the most vulnerable members. And in evolution, that matters terribly. You do not need spectacular massacre to shape a lineage. Repeated small losses, especially among the young, can be enough. The fossil record rarely gives us that process in a neat line-by-line account, but the behavioural logic is not hard to follow. Another thing worth noticing is that the social world of a dangerous primate is not calm just because its members know each other well. The same study on male baboon canines makes clear that rank depends in part on fighting ability, and that the costs of those contests can be substantial. Within-group hierarchies are therefore maintained by a mix of threat, display, memory, and occasional violence. If that is true inside the troop, one can reasonably infer how formidable such a troop might appear from the outside. A socially coordinated primate group with individuals already accustomed to dominance, submission, defence, and escalation is not a loose crowd. It is a system practiced in pressure. Dinopithecus, if it behaved in line with what its papillon anatomy suggests, would not merely have possessed sharp teeth as isolated tools. It would have embedded those teeth inside a framework of social order that multiplied their usefulness. That is one reason primate competition can feel different from carnivore predation. A predator wants the body. A rival primate may want the place, the route, the food, or the advantage of showing that it can push you. Often that is enough. So the rules of survival in this older African world begin to sound rather severe, but also very clear. Do not get isolated. Do not linger too long in exposed places. Do not assume a sleeping site is safe just because it is safer than the ground below. Do not confuse tools with invulnerability. Do not challenge an animal whose face and body are built to make challenges expensive. Read the land. Read the sounds around you. Keep to numbers. Keep the young close. Move before dark becomes someone else's advantage. For living baboons, many of these rules are visible in troop behaviour and sleeping site choices. For early Homo, the Swartkrans evidence reminds us that even clever primates with stone technology could fail to apply them successfully every time. Dinopithecus did not have to invent these rules. It was one of the animals that helped enforce them. And once the ground rules are laid out like this, the larger question starts to sharpen on its own. A very large, socially organised, broad-feeding primate with a powerful skull and formidable canines did not need to behave like a monster to become a serious problem for our ancestors. It only needed to behave like an animal, well suited to holding its ground in a dangerous landscape. That is why the possibility that Dinopithecus threatened early humans is not really a matter of dramatic imagination. It follows quite naturally from the biology. The more vulnerable the human line was, the more a creature like this could matter. Which is why, from here, it becomes necessary to look less at Dinopithecus in isolation and more at the precise ways such an animal might have pressured hominins who were still trying to stay in the game at all. What makes Dinopithecus worth taking seriously in the human story is not that we have a fossil scene of one standing over a fallen hominin like a prehistoric crime photo. We do not. There is no direct evidence that Dinopithecus systematically hunted our ancestors, and saying otherwise would be more dramatic than careful. The stronger argument is ecological. Southern Africa in the Plio-Pleistocene supported a far richer monkey fauna than today, with as many as 6 monkey species potentially living at the same time, some of them in the same ecological communities as hominins. That same review also notes that hominins occupied a generalist feeder niche that could have affected the behaviour of other primates, and that interactions may even have included predation. In other words, the scientific literature already treats hominin-monkey interaction in this landscape as something consequential rather than imaginary. Dinopithecus matters because it was one of the largest and most imposing of those monkeys. That size is the first reason it may have threatened our ancestors. Dinopithecus ingens is described as having a robust, rugged skull, a strong masticatory apparatus, a long muzzle, and a broad interorbital region, and later work continues to treat it as a very large, sexually dimorphic fossil baboon, rather than a routine member of the background fauna. Those details are not cosmetic. In a papillonin, a long muzzle means room for serious canines. A heavy chewing apparatus means a face built to process difficult foods and absorb force. And marked sexual dimorphism usually points to a social world in which male competition and physical hierarchy matter. Start with a modern baboon, increase the scale, increase the cranial mass, and place that animal in open and mixed habitats shared with smaller hominins, and the basic problem becomes obvious. You would not need direct predation to produce repeated human cost. You would need only a large, confident, socially backed primate that other animals were wise to avoid. The easiest mistake here is to think only in terms of killing. Threat is broader than that. In dangerous environments, animals shape one another's survival by controlling access to the best parts of the landscape. Modern baboon research shows that foraging party size and habitat use are strongly shaped by predation risk, and that baboons underuse food-rich places when those places are too dangerous. They choose routes, groupings, and refuges by balancing gain against threat. That means a dominant primate does not have to bite another species to harm it. It can force that species to feed in worse places, travel at worse times, drink at worse water sources, or give up good ground altogether. For early hominins, which were already living close to the edge, that sort of displacement could have had consequences far beyond a single encounter. A group that keeps yielding first choice to something bigger and more cohesive will pay for it in calories, safety and stress, and the hominins in question really were vulnerable enough for those costs to matter. South African evidence now makes it harder than ever to portray early Homo as automatically safer or more dominant than its neighbours. The 2024 reassessment of the famous Swartkrans specimen SK54 argues that it is more likely Homo than Paranthropus, and that Homo was also prey for leopards in the early Pleistocene. New 2025 work on an articulated Paranthropus robustus lower limb from Swartkrans further suggests that at least one adult individual was among the smallest known adult hominins in the fossil record, and press materials tied to that study explicitly note its likely vulnerability to predators in the Swartkrans area. Put bluntly, these were not untouchable creatures. They were small-bodied primates with tools, yes, but still very much available to the landscape. Once that scale of vulnerability is clear, modern baboons become a useful warning rather than a casual comparison. Wild baboons are not strict vegetarians quietly sampling fruit in the shade. A classic study of yellow baboons in Amboseli documented predation on vertebrates, including gazelle neonates, vervet monkeys, African hares, and bird clutches, with an estimated 91 vervet monkeys taken annually in that study population. More recent work on chacma baboons in South Africa recorded direct kills of birds, rodents, hyraxes, and juvenile antelope, including chases over open ground and attacks that began with abdominal bites. These are not giant apes taking down buffalo, but they do show something important. Baboons are behaviourally capable of opportunistic predation on vertebrates, including other primates and fast-moving prey, when the target is vulnerable enough. A larger extinct papionin does not need to be imagined as a specialist hunter for the inference to become uncomfortable. That matters especially when you consider age and isolation. In living baboons, not every member of a group is equally safe, and infants in particular run a brutal survival gauntlet. Susan Albert's summary of the Amboseli baboon research points out that first-year mortality has averaged about 30% over 4 decades, and has climbed as high as 50% in difficult times, with infant baboons needing to avoid dangers from other baboons inside and outside the group, along with disease and predation. A primate species does not need to routinely consume infants for infants to be central to its threat profile. They are simply the weakest point in the system. If Dinopithecus behaved in line with what we know from living baboons, then unattended or poorly defended young hominins would likely have represented the kind of low-cost target that can shape behaviour even when actual attacks are rare. One successful incident can alter how a group uses space for a long time afterwards. It is also worth remembering that baboon danger is social danger. A solitary animal can be frightening, a coordinated group is far worse. Modern baboons use sleeping sites strategically to reduce nocturnal predation risk, favouring safer refuges such as cliffside sites, and they adjust grouping patterns according to habitat danger. They also share information rapidly through alarm calls, displays and movement, which means threat detection and group response are often faster than a smaller, less cohesive neighbour might like. If Dinopithecus lived in the sort of structured, group-based system typical of papionins, then any encounter with it would not have been one body confronting one body. It would have been a hominin group confronting another social unit, already practiced in spacing, display, collective reaction, and local dominance. In those situations, sheer physical comparison matters less than social readiness. A troop of very large primates that knows how to surge, threaten, and hold ground does not have to win many fights to become impossible to ignore. Then there is the problem of dietary overlap. The monkey fauna review from southern Africa suggests that niche partitioning may have helped maintain high primate diversity, but it also notes that hominins in the generalist feeder niche could have affected the behaviour of other eclectic feeding monkeys. Dinopithecus itself was not a narrow specialist. Stable carbon isotope work indicates that its diet included roughly 10 to 30% C4-derived resources, more than earlier morphological expectations had suggested, which points to real use of savanna-linked foods rather than strict reliance on closed woodland fare. That kind of breadth is exactly what makes a species difficult to avoid. If hominins and Dinopithecus both exploited varied landscapes and broad food categories, then their overlap was not just geographical, it was practical. They may have wanted many of the same productive patches at many of the same times. Competition does not need identical diets to be serious. It only needs repeated pressure at the same useful places. Another reason Dinopithecus may have threatened our ancestors is that primate aggression often works by making conflict too costly to contest. In wild male yellow baboons, longer canines are associated with higher adult dominance rank after controlling for age, which suggests that weaponry and social status are tightly linked. The mouth is not just for feeding, it is part of rank, bluff, coercion, and actual violence when necessary. Dinopithecus, with a larger and more rugged cranial build than living baboons, almost certainly carried that same logic into a heavier body. A hominin group approaching a water source or feeding spot where a troop of these animals was already settled would not need a direct attack to conclude that the situation had become unprofitable. The rules of survival in such places are often conservative for good reason. If one side has more confidence, more canine display, and more physical authority, the other side usually leaves before the bookkeeping becomes bloody. That still counts as a threat. In fact, over evolutionary time, that kind of repeated forced retreat may matter more than the rare dramatic clash. There is a further complication, and it makes the whole scenario feel less cinematic but more realistic. Large primates do not only threaten through open contest, they also alter how a landscape is mentally mapped. Modern baboons avoid some rich habitats because the predation risk is too high, and they choose sleeping sites and foraging subgroups accordingly. Early hominins almost certainly had to do the same sort of mental accounting, only with a broader set of dangers. Add a giant papian into that equation, and suddenly an area may be not merely risky because of cats, but risky because cats use it, and the big monkeys get there first. That kind of layered hazard produces chronic caution. It pushes smaller groups to move more, feed faster, keep juveniles closer, or bypass otherwise valuable patches. When a lineage is small and juvenile losses matter enormously, chronic caution itself has a cost. Energy spent on avoidance is energy not spent on feeding, growth, or exploration. Dinopithecus would have been one more animal capable of imposing that tax. None of this requires us to imagine Dinopithecus as a specialised hominin hunter, and it is better not to. The most defensible picture is more measured. Dinopithecus may have threatened our ancestors because it was a very large, broad-feeding, socially organised, strongly armed primate living in the same kinds of communities as hominins during a period of environmental instability and high background danger. Living baboons show that primates of this general sort can be aggressive, opportunistically predatory, behaviourally flexible, and capable of making the landscape costly for other animals through competition and intimidation. Early hominins in South Africa were small enough, preyed upon enough, and ecologically pressured enough that those effects would not have been trivial. In a stronger, more stable lineage, the presence of such a neighbour might only have been inconvenient. In a fragile one, it could become historically important. So when the title says Dinopithecus nearly wiped out humans, the careful translation is not that one baboon species almost ended humanity single-handedly. It is that our ancestors lived in a world precarious enough for a creature like Dinopithecus to be one more serious force working against them. The threat would have come through pressure, not prophecy, through ecology, not villainy. That is what makes it worth paying attention to, because once you start thinking in those terms, the story becomes less about a single animal and more about the emotional and evolutionary consequences of living beside one. Fear, competition, caution, lost opportunities, vulnerable young, and the knowledge that a rival primate stronger than you is already using the same ground can shape a lineage one uneasy day at a time. What fear does to a species is often more important than what kills it outright. That is one of the harder lessons from primate ecology, and it matters here because the early human story in southern Africa was shaped not only by actual attacks, but by the constant need to behave as if an attack were always possible. In living baboons, predation risk measurably changes habitat use. Guy Cowlishaw's work on desert baboons showed that they do not simply feed wherever food is richest. They trade foraging gain against danger, which means some good feeding areas are underused because the risk attached to them is too high. Research on baboon sleeping sites shows something similar at night. Baboons favour refuges that reduce predator access, change their behaviour after predator encounters, and use sleeping decisions as part of an anti-predator strategy, rather than as a casual matter of convenience. Fear, in other words, is not just a feeling in primate life. It is a scheduling system, a map, and a set of repeated adjustments about when to move, where to stop, and what not to risk. That matters because the first humans in this landscape were not living above those rules. They were living inside them. Around 2 million years ago, South Africa was not home to one clear and uncontested human form, but to an unusually diverse hominin scene. Work at Dreamelin indicates that Australopithecus, Paranthropus, and early Homo overlapped in South Africa at about this time, and the authors argue that the high taxonomic diversity on the South African landscape around 2 million years ago was likely a response of hominins and other fauna to climate and environmental instability. That should immediately make us more cautious about telling the story as if the human line was already secure. It was not secure. It was branching, overlapping, and subject to the same environmental sorting process that was affecting many other mammals. A fragile human line does not mean modern humans were nearly erased in one dramatic instant. It means the broader hominin presence in these southern African ecosystems was still conditional, still local, and still capable of failing. The evidence for vulnerability becomes even sharper when we look at predation directly. The famous SK54 cranium from Swartkrans has long been linked to leopard predation, and a 2024 reassessment argues that the specimen is more likely Homo than Paranthropus. The significance is hard to miss. For a long time, one influential reading of the Swartkrans evidence encouraged the idea that early Homo, because of greater technological or behavioural sophistication, was better at avoiding predation than Paranthropus. But if Homo itself was prey for leopards in the early Pleistocene, that tidy contrast weakens considerably. The old landscape was not neatly divided into clever survivors and clumsy victims. Even the lineage most often cast as the rising winner was still exposed enough to be carried off. That fact does not just add drama, it changes the scale of the problem. If Homo could be prey, then danger was not waiting politely at the margins. It was already participating in the daily arithmetic of survival. Now place that fact beside what we know about baboon life, and the idea of fear starts to become more concrete. Predation risk is not only something that occasionally removes individuals, it also helps determine how many individuals a primate group needs to function in the first place. Comparative work on baboons has found that minimum group size is related to predator density and female body mass, reinforcing the long-standing view that one of the central benefits of living in larger groups is reducing predation risk to an acceptable level. That does not mean more bodies always solve the problem. Large groups also bring competition, coordination costs, and stress. But it does mean that medium-sized terrestrial primates are pushed by danger into social solutions. If early hominins were facing similar pressures, and much of the South African evidence suggests they were, then fear would not merely have influenced a few bad days. It would have helped shape how groups were formed, when they moved, how many individuals stayed together, and what counted as viable social life in exposed country. This is where competition enters the story, because fear is often made worse by the fact that the safest choices are not always the most productive ones. Cowlishaw's work on baboons showed that food-rich habitats may be used less than expected when predation risk is high. In practical terms, that means danger can force primates into poorer feeding situations even when better options are visible and nearby. Add a large, socially organised, heavily armed papionin like Dinopithecus to that kind of environment, and the problem multiplies. A dangerous carnivore can scare you away from a place because you might be eaten there. A powerful rival primate can scare you away because it is already there, because it can physically dominate the situation, or because it can raise the cost of staying until the food is no longer worth the confrontation. The result is the same in one crucial sense. Your group feeds elsewhere, later, faster, or less well. If this happens often enough, the cost is cumulative rather than theatrical. And cumulative costs are how fragile lineages get bent out of shape. Dinopithecus fits that logic almost too well. It was a very large, sexually dimorphic fossil baboon with a robust skull and a strong masticatory apparatus, and researchers continue to treat it as a distinctive large-bodied papionin in the South African record. It also appears to have had a broad feeding ecology, including real use of savanna-based C4 resources rather than strict dependence on one narrow habitat type. That means it was not just big, it was flexible. It could move through the same general landscapes as hominins and draw food from some of the same broader resource zones. In ecology, that combination is often more consequential than a single dramatic trait. A large specialist may dominate one corner of the system and vanish when conditions shift. A large generalist can remain a nuisance almost everywhere. For early hominins already making trade-offs between food and safety, Dinopithecus would not have had to launch constant attacks to become a serious presence. It could simply have been one more strong, confident claimant on the same ground. Modern baboons also remind us that primates can be dangerous in ways that do not fit the usual herbivore versus predator categories. Field studies of yellow baboons in Amboseli documented predation on vertebrates including neonate gazelles, hares, birds and vervet monkeys, while more recent work on chacma baboons in South Africa has recorded kills of birds, rodents, hyraxes and juvenile antelope, and these are opportunistic patterns, not evidence of a specialised hunting lifestyle. But that is exactly why they matter here. Opportunistic predation is often enough to reshape another species' behaviour. If a large papionin will sometimes chase, seize, or kill vulnerable vertebrates when circumstances are favourable, then infants, juveniles, or isolated members of another primate species become part of the risk environment even if they are not regular prey. For a hominin group with slow reproduction, long dependency and high investment in offspring, even low-frequency events of that sort could weigh heavily. One successful attack can become a lesson that reorganises movement and vigilance for a very long time afterward. That is especially important because infant and juvenile survival is where primate populations are often thinnest. Susan Alberts' summary of the Amboseli baboon project notes that a wild infant baboon has to learn to identify and consume hundreds of foods while avoiding dangers from other baboons, disease and predation, and that first-year mortality has averaged about 30% over 4 decades, rising to 50% in difficult times. Other long-term work from the same system notes that only about half of live-born females and fewer than half of live-born males survive to adulthood. Those numbers are not being offered as direct hominin measurements, because they are not. They are useful because they reveal just how narrow the margin can be for long-lived terrestrial primates, even in a species already well adapted to its environment. If a well-established baboon population loses infants and juveniles at that rate, then early hominin groups facing predators, competition, and environmental instability would have had no excess margin to waste. Fragility in such a system is not metaphorical, it is demographic, and the effects of early hardship do not stop in infancy. Longitudinal work in wild baboons has shown that cumulative early adversity predicts substantially shorter adult lifespan, with females experiencing 3 or more adverse conditions dying a median of 10 years earlier than females exposed to 1 or none. Again, we should not pretend that this gives us a direct mortality table for Australopiths or early Homo. What it does give us is a sober model of how pressure accumulates in long-lived social primates. Poor maternal condition, social instability, ecological difficulty, threat, and repeated disruption do not just remove individuals at the moment they occur. They cast a shadow forward. They shape later survival, reproduction, and resilience. When the human line is described as fragile, this is the kind of fragility worth imagining. Not a glass object waiting for one blow, but a slow primate lineage absorbing many small costs that shorten lives, reduce successful reproduction, and make bad years more dangerous than they would otherwise be. In that kind of system, an intimidating rival primate can matter even without spectacular violence. Fear also changes where the weak members of a group end up. A recent study on individual exposure to predation risk in group-living baboons showed that age and social position affect who ends up in at-risk locations within the group, reinforcing the broader point that risk is not evenly distributed even among animals moving together. Some individuals, by age, rank, or simple position, are more exposed than others. That is almost certainly true for hominins as well. A group travels at the speed of its most vulnerable members, but it does not protect those members equally well at every instant. Youngsters lag, mothers are burdened, injured individuals alter routes. Sleeping sites may be chosen for the group, but attacks happen to bodies. Once you think in those terms, the presence of Dinopithecus becomes more serious. Its threat would not have fallen evenly on humans as a category. It would have fallen hardest on the smallest, slowest, youngest, or most isolated individuals, which is exactly how population-level damage often begins. Competition, meanwhile, would have worsened all of this by taking away the comfortable assumption that danger only arrives in the form of teeth from above. The same South African monkey fauna review that places Dinopithecus in a more diverse Plio-Pleistocene primate community argues that hominins likely affected monkey behaviour through niche overlap and perhaps predation, which means the reverse possibility also deserves attention. These were not separate stories unfolding in parallel. They were entangled primate communities. A large pepionin and a small hominin group might both value a sheltered route, a productive patch, or a water-adjacent feeding area for overlapping reasons. The difference is that one of those primates may have carried more physical authority into the dispute. Over time, repeated disadvantage in such encounters could lower returns, increase travel, and raise the stress of ordinary movement. Fear and competition in that sense are not separate pressures. Fear is often what competition feels like when the other claimant is stronger. This is why the fragile human line should not be imagined as a straight path lightly troubled by a few colourful enemies. It was a cluster of populations and lineages persisting under pressure while the environment itself was changing around them. Some of those lineages disappeared, some endured longer. One eventually led to us, but that ending was not visible from the ground. From the ground, what existed was risk management. Stay together enough to matter, but not so large that feeding becomes impossible. Choose safe sleeping places, though none are completely safe. Reach good resources, though someone stronger may already be there. Raise young in a world where even success is partial, and every season rewrites the numbers. That is the setting in which Dinopithecus becomes historically interesting. Not as a single destroyer, but as part of the machinery that kept the human future uncertain. And because that machinery was not only biological but environmental, the next thing to understand is how a changing climate could make all of these pressures sharper at once, turning an already hard world into an even harsher one. And once fear has become part of daily behaviour, climate starts to matter in a different way, because a dangerous landscape becomes far worse when it refuses to stay the same. The older South African world was not simply hard in one consistent, reliable fashion, it was shifting. Rainfall patterns changed, vegetation boundaries moved, faunal communities were rearranged, and the places that were useful in one stretch of time did not necessarily remain useful in the next. A recent broad review of the cradle of humankind notes that most of its fossil-bearing deposits fall between about 3 and 1.4 million years ago, and that faunal reconstructions across sites commonly show a trend of wooded landscapes giving way to grasslands. The same review also notes evidence from microfauna and birds, pointing toward a gradual move to more grassland-dominated conditions, even if the exact timing of that shift remains difficult to pin down. In simple terms, the ground under these animals was not becoming a uniform desert, but it was becoming more open in important ways, and openness changes everything for primates. That last point deserves a slower look, because when people hear climate change in prehistory, they often imagine a smooth one-way slide from forest to savanna, as if nature had politely followed a single instruction manual for millions of years. The South African record is messier than that. A 2025 reconstruction of cradle paleoclimate using faunal remains and machine learning found no progressive shift toward aridification over the last 3.5 million years, while also suggesting that annual precipitation was lower than today, and that many sites occupied an ecotone between grassland and open savanna. That is a useful correction. It tells us the story is not simply one of ever-increasing dryness. At the same time, local faunal and isotopic work still points to recurrent openness, lower rainfall than modern conditions, and repeated movement toward grassland-rich settings. The better picture is not monotony, but instability, not a single climate sentence repeated forever, but a long argument between wetter and drier phases, wooded pockets and open country, stable refuges and expanding exposure. That is exactly the kind of climate story that creates harsh worlds for primates. Forests and closed woodlands offer cover, vertical escape, shade, and a different pattern of food opportunities than open ground. Grasslands and open savannas offer visibility and access to other kinds of resources, but they also reduce concealment, increase travel exposure, and often tie safety more tightly to group size, vigilance, and timing. For a large terrestrial papionin like Dinopithecus, some of that openness may have been manageable or even useful. For small hominin groups carrying infants, experimenting with tools, and already watching for leopards and other carnivores, more open country could make ordinary movement substantially more expensive. The South African cave record keeps pointing toward mosaic settings rather than a single habitat type, which means these animals were rarely dealing with a stable answer to the question of where to feed and where to sleep. They were dealing with mixed landscapes whose risk profile could shift across fairly short distances and over longer climate cycles as well. Some of the strongest evidence that this was not a gentle background trend comes from the period around 2.3 to 2.0 million years ago. Work at Drimolen argues that while an overall trend toward aridity occurred, this interval was a critical period of major ecological change and dispersal that extensively modified South African faunal communities. The same paper links the transition to broader regional evidence. Deep-sea cores off Namibia indicate stronger climatically induced fluctuations between 2.7 and 2.2 million years ago, with semi-arid environments more widespread during glacial periods, and aridification plus climate variability increasing significantly after 2.2 million years ago. Yet even that was not uniform across the subcontinent, because the authors also note humid conditions in the Limpopo Basin between 2.0 and 1.75 million years ago. This is one of those cases where the details matter more than the slogan. The world was not simply drying, it was fragmenting into more uneven ecological opportunities, with some places becoming harsher, some remaining productive, and all of it happening quickly enough to reshape communities. When researchers try to read those changes in the caves themselves, they find similar signs of an environment losing some of its old predictability. The Drimolen paper points out that major phases of massive speleothem and tufa deposition in the Pliocene at sites such as Makapansgat limeworks and Taung gave way to increasingly sporadic formation through the Pleistocene, which is exactly the sort of geological detail that sounds dry until you realise what it implies. Long, sustained wet conditions suitable for heavy cave mineral deposition were becoming less dependable. Water was still present, of course, but the rhythm had changed. In a living ecosystem, that kind of hydrological instability is felt everywhere. Water sources become less reliable or more seasonal. Plant communities reorganize. Herbivores track those changes. Carnivores follow the herbivores. And primates who need food, water, social cohesion, and safe sleeping locations all at once end up trying to solve a moving puzzle that seems determined to alter the pieces halfway through. The animal communities responded in ways that make the landscape feel even more unsettled. Drimolen is described as recording a transitional faunal community overlapping between older sites, such as Sterkfontein Member 4 and Makipanskat Limeworks, Member 3, and younger sites such as Swartkrans and Gondolin. The same authors say this reflects a larger turnover in mammal communities driven by major ecological changes in southern Africa, including the extinction of South African endemic species, the dispersal of new species, and adaptive radiation in the region. That is a very plain way of saying the old order was being broken up. Familiar animals disappeared, new arrivals moved in, some lineages diversified in response. South Africa during the early Pleistocene was not merely a refuge, it was also a sorting ground. And for hominins, that meant any adaptation that worked in one ecological arrangement had to survive contact with the next one. This is why climate change in this story cannot be treated as a distant backdrop while the animals do all the real work in the foreground. Climate was helping decide which foods were available, which routes stayed viable, which water sources attracted competition, and which habitats became easier or harder for different species to use. At Swartkrans, for instance, the faunal evidence has long been read as suggesting a generally more open environment than Sterkfontein Member 4, with species indicating wooded grassland, rocky hills, and riverine woodland savanna nearby. Later isotopic work summarised in the recent Cradle Review notes that Swartkrans Member 1 may represent a mosaic or C4 wooded grassland, while Members 2 and 3 were more heterogeneous with less C4 influence, and that some studies suggest increased grass presence after about 1.7 million years ago. None of that yields one clean environmental sentence. What it yields is variation, and variation is precisely the sort of thing that makes life hard for lineages trying to settle into efficient routines. For early humans, that would have changed the meaning of ordinary tasks. A route that once combined cover, food, and a tolerable level of predator exposure might later become too open. A feeding patch that once justified the trip might become poorer or more contested. Sleeping places that worked in wetter or more wooded conditions might become less secure if the surrounding vegetation shifted, or if the density and movement of other animals changed around them. Modern baboon studies show how strongly primates respond to risk in their decisions about foraging and sleeping. Put those same kinds of decisions into a climate system that keeps reshaping the landscape, and the result is not just more hardship in a vague sense, it is constant recalculation. Where do we go now? Is the old place still good enough? Is the water still worth the approach? Has the cover thinned too much? Is the food there? And if it is, who else has noticed? Those are climate questions at ground level, even when they sound like behavioural ones. There is also a temptation to assume that if environmental variability was important, it must have worked like a direct lever on evolution, increasing or decreasing species almost mechanically. The broader African record advises caution there. A 2022 PNAS synthesis found strong evidence for orbital forcing of environmental variability across the Plio-Pleistocene, superimposed on a longer trend of increasing variability, but it did not find a significant correlation between that variability and mammalian speciation, or extinction rates at regional and basin scales. In other words, climate variability clearly mattered, but not in a simple puppet master way where every spike in instability produces a neat evolutionary result. That nuance actually helps the story here. It suggests that harsh climates shape life through local ecological consequences and behavioural pressures rather than through an automatic one-to-one rule. So when we talk about climate making the world harsher for early hominins and Dinopithecus alike, the point is not that every rainfall oscillation created a new species or killed one off on schedule. The point is that changing conditions altered local survival problems continuously and unevenly. That unevenness may have been especially important in South Africa, because local records do not always line up neatly with continent-wide trends. The 2025 cradle reconstruction explicitly notes that temporal correlations between global climate change patterns and local environmental proxies from hominin-bearing deposits are not always verifiable. That sounds technical, but it has a very practical consequence for how we imagine this ancient world. A broad African trend toward greater variability, or more open ecosystems, does not tell you exactly what an animal at Swartkrans or Drimmelen faced in a given valley or season. Local topography, groundwater, vegetation mosaics, and faunal community structure all matter. So did the fact that caves and their surrounding catchments gathered bones over long stretches of time, often under varying climatic regimes. The cradle record can therefore preserve the signature of multiple ecological states layered into the same general area. That makes simple stories satisfying, but wrong. The real world these hominins inhabited was likely patchier, more local, and more unpredictable than any single climate curve can capture. Still, patchiness is not a comfort if you are small and vulnerable. In some ways it makes things harder. A uniformly bad landscape can at least be understood. A mosaic landscape with shifting wet pockets, open stretches, wooded corridors, and changing seasonal returns forces animals to make more decisions, and decisions are where mistakes happen. A place that stays useful may also attract more competitors. A patch of reliable water during drier intervals becomes a meeting point for herbivores, carnivores, large monkeys and hominins alike. A strip of woodland in an otherwise more open setting can become both refuge and trap. Dinopithecus, with its probable terrestrial habits and flexible diet, may have been well placed to exploit this sort of mixed terrain. Early hominins, too, were trying to do exactly that. Climate change then did not just change the weather around them, it intensified overlap. It funneled animals toward the same good places and made the bad places more costly to use. That is how a hard world becomes a harsher one without needing any single apocalyptic moment. And once overlap intensifies, the whole question of competition becomes sharper. Dinopithecus was not an animal confined to one fragile dietary niche. Isotopic work suggests it used savanna-linked resources more than earlier morphological expectations had predicted, which implies a broader ecological reach. Hominins were also generalists in their own way, moving through mosaic habitats, using tools, and trying to draw food and opportunity from different parts of the landscape. In a stable world, two flexible primates might partition resources enough to coexist with tolerable friction. In a world turning harsher, even modest overlap can become serious. Scarcer or more seasonal resources raise the value of access. Safer routes become more contested. Marginal habitats become necessary rather than optional. The practical outcome is that climate pressure can make rival species more troublesome without changing anything about their underlying temperament. An ordinary competitor in a good year can become a dangerous one in a bad year. There is another effect climate instability tends to have on primate life, and it is less visible but deeply important. It shortens the margin for error in reproduction. Long-lived primates do not replace losses quickly. They depend on surviving adults, protected juveniles, and enough reliable food to support prolonged development. If rainfall becomes less predictable, vegetation patches shift, and high-quality feeding zones become harder to reach or more contested, then mothers and infants bear some of the earliest costs. This is one reason harsh climates feel so cruel to primate lineages. They do not always kill dramatically. They wear away the conditions needed to raise the next cohort successfully. In a fragile hominin population, that sort of pressure would have interacted with predation, competition, and the general danger of the landscape in ways the fossil record can only show indirectly. But indirect does not mean trivial. A lineage can begin to fail quietly long before anyone would have named the cause. So when we say the world was turning harsh, the phrase should be taken literally but not simplistically. It was not a single march toward dryness, and it was not a universal collapse everywhere at once. It was a period in which increasing variability, more frequent openness in some areas, lower precipitation than today, local wet and dry contrasts, and substantial faunal turnover combined to make the southern African landscape harder to read and harder to trust. For the human line, that meant survival had to be negotiated under conditions that were already unstable before any leopard appeared or any rival primate troop arrived. For Dinopithecus, it meant living in the same unsettled system and, for a time, managing it well enough to remain one of the major primate presences on that land. But climates that create powerful animals can also remove them. A creature can be well built for one version of a world and poorly suited for the next. And that is where this story begins to turn, because once the environment stops offering the same opportunities it once did, even giants start to find that survival is no longer as straightforward as strength made it seem. That is where the story begins to turn, because a giant can dominate a landscape for a while and still fail to outlast the landscape that made it. Dinopithecus does not disappear from the fossil record in the satisfying way stories often prefer. There is no clean final scene, no last stand, no evidence of one dramatic collapse. What the record gives us instead is a narrowing of presence. Dinopithecus ingens is securely an early Pleistocene animal in South Africa, known especially from sites such as Swartkrans and Swartkrans, and faunal biochronology places the Swartkrans member 1 record at roughly 2.1 to 1.7 million years ago. After that, the trail becomes quiet. That silence matters, but it has to be read carefully, because in paleontology, silence is rarely as simple as absence. Fossils are patchy, caves are complicated, dating has long been difficult, and fossil monkey taxonomy in South Africa is famously untidy. Even so, the broad pattern is clear enough to trust. Dinopithecus belongs to an older, more diverse primate world than the one that survives in southern Africa today. One of the most useful things we can say at the outset is that the disappearance of Dinopithecus was likely slow, because the whole monkey community around it was changing slowly as well. Sarah Elton's review of the southern African monkey fauna emphasises that modern species represent only a small part of the diversity that existed in the Plio-Pleistocene, when 11 Cercopithecid species were present, and as many as 6 may have been contemporaneous. The same review argues that movement toward more open environments, together with dispersal into and out of southern Africa, probably contributed significantly to changes in monkey diversity over the last 3 million years. That is not the description of one animal suddenly hitting a wall. It is the description of a long ecological reshuffling, in which some lineages held on, some diversified, and some gradually lost their place. Dinopithecus seems to have been one of the latter. This is important because the animal itself looks, at first glance, like the sort of creature that ought to endure. It was very large, sexually dimorphic, and cranially powerful, with a kind of rugged skull and strong masticatory apparatus that suggests toughness, flexibility, and a life spent solving hard problems successfully. But strength in evolution is always conditional. Dinopithecus was not strong in the abstract. It was strong in a particular South African setting, one that appears to have included mosaic habitats, open grassland components, wooded zones, and the kind of ecological overlap that allowed several large-bodied papillonins to coexist for a time. In a 2020 review of baboon evolution, Sarah Elton and Jason Dunn describe Papio as originating in the early Pleistocene and later radiating into the modern baboon diversity we know today. In the same broader body of work, the Southern African fossil record comes through not as a single steady baboon lineage, but as a brief radiation of large-bodied terrestrial monkeys without a modern equivalent. Dinopithecus was part of that radiation, and brief is the word that matters. Brief radiations are often a sign that a lineage was successful under certain conditions, but did not establish a lasting hold once those conditions shifted. That fits rather well with the climate story from the cradle of humankind. The 2025 Quaternary Science Review's reconstruction found no simple progressive march toward aridification across the last 3.5 million years, but it did find that annual precipitation was lower than today and that many sites occupied an ecotone between grassland and open savanna. The authors also warn that temporal correlations between global climate patterns and local proxies in hominin-bearing deposits are not always straightforward. That does not weaken the case for environmental stress, it refines it. It tells us that Dinopithecus was living through local ecological instability rather than one tidy climatic slogan. A species adapted to mixed, shifting, competitive ground may persist for a while under those conditions, but if the balance between habitat types, water reliability, and community structure keeps changing, then well-adapted can slowly become no longer best placed. The large mammal review of the cradle, published in 2025, helps fill in what that would have looked like on the ground. The authors conclude that most major cradle deposits date between about 3 and 1.4 million years ago, and that faunal-based paleo-environmental reconstructions commonly show a trend of wooded landscapes giving way to grasslands. That does not mean every site or every interval followed one exact ecological script, but it does support a wider picture in which the southern African world of the early Pleistocene was gradually becoming more open in ways that mattered to large mammals and primates alike. For Dinopithecus, a large terrestrial papionin that may not have been catastrophic at first, open settings can favour large ground-dwelling monkeys, but the problem is that more openness is not the same as stable opportunity. Open country changes predator dynamics, resource distribution, travel costs, and niche overlap. When those pressures build together over long enough time, being big may stop being the advantage it once was. There is another possibility worth considering, and it comes from competition rather than climate alone. The same 2020 Baboon review notes that Papio originated in the early Pleistocene and later spread into multiple species, while estimated ancestral ranges place the origin of Papio in South Tropical Africa rather than the far south, followed by movement south and west. That suggests the southern African papionin scene was not closed or static. New baboon forms were moving, diversifying, and exploiting available niches. If Dinopithecus belonged to an older, large-bodied radiation, then one plausible reason for its eventual disappearance is that it was overtaken not by a single enemy, but by a changing primate field in which Papio and other papionins were better matched to the emerging conditions. Evolution does not always remove a species because it fails dramatically. Sometimes it removes a species because a relative with slightly different scaling, dispersal, or ecological tolerance does the same job more efficiently. That kind of replacement, though, is hard to prove directly, and this is where the fossil record starts to insist on humility. The 2017 Paleontologia Electronica study on South African fossil monkey cranial variation is quite blunt about the problem. It notes that cave system geology makes chronometric dating difficult, that monkey fossils have often been used as biochronological markers because of that difficulty, and that many of the South African fossil papionins are quantitatively and qualitatively similar to extant Papio. More importantly, the authors found that many cranial measurements are so strongly correlated that they fail to distinguish species or even genera of fossil papionins reliably, and they conclude that extinct taxa may not be discriminable using craniofacial measurements alone, or that current taxonomic designations are confounded. They also note that some genera, including Dinopithecus, are represented by only a handful of specimens. That means the slow disappearance of Dinopithecus is partly a biological story and partly a visibility problem. We're trying to watch an extinction through a foggy window made of a few skulls, difficult cave dating, and an argument about what counts as one genus in the first place. Still, foggy does not mean featureless. Even allowing for taxonomic difficulty, the broad direction of change remains visible. The monkey fauna of southern Africa became less diverse than it had been in the Plio-Pleistocene, and the peculiar crowd of large-bodied terrestrial papionins that once included Dinopithecus did not survive into the modern fauna. Today, southern Africa has baboons, vervets, and a more limited set of monkey forms compared with the richer, stranger primate communities preserved in the fossil caves. That is genuine evolutionary narrowing. The question is not whether Dinopithecus vanished. It did. The question is, what combination of pressures made its disappearance more likely? On the available evidence, the best answer is an interaction of environmental change, shifting community structure, dispersal and radiation of other papillonins, and perhaps the simple cost of being a very large primate in a world where ecological certainty was fraying. Body size itself may have contributed to that vulnerability. Large animals often enjoy competitive advantages while conditions suit them, but they also tend to carry higher energetic demands, longer developmental schedules, and lower tolerance for prolonged resource shortfalls. We cannot measure Dinopithecus metabolism directly, of course, but we do know it was a very large papillonin, and we know from the cradle climate and faunal literature that habitats, rainfall and community composition were changing through the interval in which these fossils occur. A broad-feeding terrestrial generalist can buffer some of that variability, and Dinopithecus probably did. Stable isotope and dental evidence from earlier studies suggest it was not a narrow specialist. Yet generalism has limits. If productive patches become more contested, if safe movement routes shift, if predator and competitor pressure change together, then even a flexible lineage may find itself paying more than it can recover. The slow disappearance of a giant often looks, from the inside, like a sequence of increasingly expensive years. It is also possible that the same qualities that once made Dinopithecus formidable made it less adaptable later on. A large-bodied, socially complex, heavily built papillonin may do extremely well in open and mixed country, when troop life, food access, and predator avoidance line up in its favour. But those same animals can be tied to particular movement patterns, sleeping site strategies, and ranges that are not infinitely adjustable. Smaller or differently proportioned baboons may have had an easier time tracking emerging mosaics, dispersing through changing landscapes, or exploiting new combinations of foods and microhabitats. The fossil record cannot show us the exact troop-by-troop decisions, but modern primate ecology gives us a strong hint about the principle. Species do not respond to habitat change as blank slates. They respond through bodies and behaviours already in place. If the new world rewards a different package, the old package fades, even if it was impressive. There is a quieter possibility too, and it may be the most realistic of all. Dinopithecus may not have vanished because one thing went wrong, but because too many things became slightly less right. A little less reliable water, a little more openness in the wrong places, a little more pressure from other baboon-like primates, a little more competition around the best patches, a little less resilience when bad seasons came in sequence, a little more demographic vulnerability in a slow-breeding primate lineage. Extinction often works that way. It is not always a cliff. Sometimes it is erosion. A species becomes less common, then more restricted, then absent from the places where it once held ground, and only much later does the fossil record allow us to say that it is truly gone. The fact that Dinopithecus is known from such a limited set of fossils and remains absent from the later, more familiar primate communities of southern Africa makes that erosional model feel entirely plausible. What is striking, though, is not merely that Dinopithecus disappeared. Many species do. What is striking is that it disappeared from a region where it had once been part of a primate world, richer and more intimidating than the modern one. It belonged to a southern African setting where several monkey species coexisted, where some of those monkeys were very large and terrestrial, where hominins were also present, and where the environment was dynamic enough to keep resorting the whole community. Dinopithecus, for a time, seems to have been one of the primates built to thrive in that difficult world. Then the world kept changing. Other baboons rose. The broader monkey fauna was reduced and reorganized. The giant slipped out of the record. That is not a dramatic ending, but it is a very evolutionary one. The landscape that once made you formidable does not promise loyalty, and perhaps that is the most useful way to understand its disappearance. not as failure in any simple sense, and not as proof that our ancestors had somehow outmatched it in a direct contest, but as a reminder that the early Pleistocene was sorting everyone at once. Hominins were being tested, carnivore guilds were being tested, monkey communities were being tested. Dinopithecus was not removed from history because the story no longer needed it. It was removed because the ecological arrangement that supported it did not last. What remains, then, is not the animal itself, but the evidence we can still gather from the pieces it left behind, and that evidence has a way of forcing us back toward caution. Because once a giant fades into a fossil record this fragmentary, the real question is no longer simply why it vanished, but how much the fossils truly allow us to say at all. By the time we get to this point in the story, it helps to stop and ask a stricter question. What do the fossils actually show, and what are we adding because the gaps make us uncomfortable? Fossils are powerful, but they are not generous in every direction. They do not give us a complete animal walking across a plain in good light with a handy label attached. They give us pieces, context, comparisons, and probabilities. In the case of Dinopithecus, those pieces are enough to say that a very large baboon-like primate really did live in early Pleistocene South Africa, and that it belonged to the same broad world as early hominins. The type material traces back to ex situ breccias collected by Robert Broom in the Scherverberg region, and later occurrences are associated especially with Swartkrans member 1 and also Sterkfontein member 4 in the wider South African record. The larger Cradle review also makes clear that these cave systems are rich but complicated, with long histories of excavation, difficult depositional histories, and dates that have often been revised as methods improved. So the fossils do tell us Dinopithecus was real, but they also tell us right away that this is not the sort of animal we know from a neat, complete skeleton in one perfectly dated layer. The first strong thing those fossils tell us is what sort of primate we're dealing with. Even older summaries note that the morphology of the skull and teeth of Dinopithecus ingens is most like that of Papio, in other words the baboon side of the African Papionin family tree, and later cladistic work places Dinopithecus among crown African Papionins or very close to them. That is important because it keeps us from imagining the wrong animal. Dinopithecus was not some mystery beast halfway between gorilla and monster. It was a monkey, closer in overall cranial logic to baboons than to apes, though very large and somewhat unusual within that broader group. The fossils therefore anchor the reconstruction to something biologically sensible. When we imagine Dinopithecus, we should be thinking in terms of an outsized, rugged, baboon-like primate, rather than inventing something wholly unfamiliar. The bones do not support fantasy. They support a grounded primate with a strong place in Papionin evolution. They also tell us that size was one of its defining features, though here the fossils immediately force some caution. Dinopithecus appears in comparative studies as one of the larger South African fossil Papionins, and in the Monson et al.'s cranial dataset it sits among the largest skulls in the sample. At the same time, that same study warns that many fossil Papionin cranial measurements are strongly correlated and often fail to distinguish cleanly between taxa. Size matters, but size can also confuse taxonomy if it is treated too casually, so the correct reading is not that the fossils hand us one exact body weight and a perfect silhouette. What they show is that Dinopithecus was very large relative to many other Papionins, large enough that body size itself became part of the taxonomic and ecological conversation. That is a robust conclusion. The more dramatic claims sometimes made in popular writing are less secure. Fossils are very good at telling us large and imposing. They are less good at letting us announce a single definitive mass with theatrical confidence. The next thing the fossils tell us, and this is where the reconstruction becomes both stronger and more limited at the same time, is that most of what we know comes from heads. Dinopithecus is overwhelmingly a craniodental animal in the record. Monson and colleagues included 5 diphthong specimens of D. ingens from Swartkrans in their cranial analyses, and they explicitly note that juvenile SK554 was included because it is the most complete cranial specimen representing the genus in that sample. The Ditzong archive itself lists SK554 from Swartkrans member 1 as a partial cranium, not a full skeleton, and older comparative work notes bluntly that there are no postcranial specimens of Dinopithecus with which to compare material from elsewhere. That matters more than it may sound. A skull can tell you a tremendous amount about diet, relationships, sexual dimorphism, and likely social display. It cannot tell you everything about limb proportions, gait, climbing ability, or the exact balance between terrestrial and arboreal behaviour. So the fossils do give us Dinopithecus, but they give it to us mostly from the neck up. That skull-heavy record is still revealing. From craniodental work, Dinopithecus emerges as a robust, heavy-faced animal with a strong chewing apparatus, long muzzle, and broad area between the orbits. Even when researchers disagree about genus boundaries or allometric effects, they do not tend to describe Dinopithecus as a delicate or gracile form. The cranial architecture consistently points toward an animal built for forceful processing of food and for the social signalling that large muzzles and canines make possible in papionins. In practical terms, the fossils support an animal that would have looked imposing before it even moved. A long baboon-like face, heavy jaws, and the probable canine display associated with that sort of anatomy are not minor details. They tell us that Dinopithecus was built in the general mould of a serious terrestrial papionin, one whose head was both a feeding machine and a warning structure. What the fossils do not tell us is exactly how much of that impression translated into day-to-day aggression, because behaviour leaves a lighter trace than bone. The fossils also tell us where Dinopithecus sat in time, though not always with the precision we might like. The broader Cradle Review emphasises that exact ages and depositional histories in these cave systems have historically been difficult to assess, and that many faunal reports are old and need more review or reanalysis. For Swartkrans member 1, however, the picture is good enough to be useful. The lower bank has returned dates around 2.2 million years, with primate-based estimates for member 1 in the general range of about 2.0 to 1.8 million years, while the hanging remnant falls into a slightly later but overlapping early Pleistocene window. That lets us say Dinopithecus belonged to the same broad chronological world as early Homo and Paranthropus robustus at Swartkrans and nearby South African sites. The fossils therefore do not place Dinopithecus in some separate, romantic prelude before humans arrived. They place it in the same rough landscape and time frame as some of our early relatives. Site associations carry another piece of the story. The fossils tell us Dinopithecus was part of a primate community, more diverse than the one in southern Africa today. The Cradle Review notes Dinopithecus ingens from Sterkfontein, member 4 alongside 3 Parapapio species, and Cercopithecoids williamsi, while the broader monkey fauna synthesis for southern Africa argues that Plio-Pleistocene communities could include many monkey species living at the same time, some in the same ecological settings as hominins. This matters because fossils are not just isolated animal names. They preserve community structure. Dinopithecus was one primate among several, and that already tells us something important about the kind of environment it inhabited. It lived in a monkey-rich, predator-rich, hominin-bearing world where ecological overlap was normal. That is one of the reasons it makes sense to discuss Dinopithecus as part of the pressure system around early humans. The fossils do not show us an encounter. They do show us that the cast of possible encounter was very much present. Then there is diet, and here the fossils become more generous again because teeth can preserve wear and chemistry, in ways that turn them into surprisingly good ecological witnesses. Stable carbon isotope work on South African fossil baboons found that Papio, Dinopithecus, ingens, used more savanna-based C4 resources than earlier predictions based on molar morphology had suggested, particularly in the case of Dinopithecus. That's a strong result because it tells us the animal was not as tied to one narrow feeding niche as some older dental expectations implied. Microwear work, meanwhile, suggested a broad feeding pattern rather than a highly specialised one, Put simply, the fossils tell us Dinopithecus was probably not a picky specialist surviving on one fragile category of food. It seems to have been a flexible feeder with a mixed ecological reach. That is exactly the sort of information fossils can reveal very well, because teeth interact directly with food and preserve the consequences of that interaction in measurable ways. But for every one of those useful inferences, there is another question the fossils cannot settle cleanly. They cannot tell us fur colour. They cannot tell us the sound of its alarm calls or threat vocalizations. They cannot tell us whether males had a particular crest of hair or how quickly a troop moved across broken ground in the early morning. Even locomotion remains less certain than many popular depictions imply, because again, there are no confidently attributed postcranial remains of Dinopithecus on which to base a full mechanical reconstruction. Terrestriality is a very reasonable inference for a large papillonine of this sort, and many researchers do infer it. But it remains an inference built from size, relationships, and ecological context rather than from a complete limb skeleton. This is one of the clearest examples of what fossils really tell us. Not nothing, but not everything either. They let us draw an increasingly well-supported silhouette, while many of the vivid details remain beyond direct recovery. Taxonomy is another place where the fossils teach humility. The South African Papillonian record has been described in the literature as complicated and confused, and Monson and colleagues go even further, arguing that many cranial measurements fail to distinguish fossil Papillonian species, and even genera as cleanly as they distinguish living ones. They conclude that extinct Old World monkey taxa in this record may not be discriminable using craniofacial measurements alone, or that the current taxonomic designations are confounded. They also point out that some genera, including Dinopithecus, are represented by only a handful of specimens. That does not mean Dinopithecus is imaginary or meaningless. It means the fossil record is forcing us to be careful about how sharply we draw lines between some extinct baboon-like monkeys. It also means that every new reanalysis has the potential to shift the labels slightly, without changing the broad ecological picture very much. The bones tell us there was a big, distinctive papillon in here. They also tell us classification in this group is not a solved puzzle. The same caution applies when people want the fossils to answer the most exciting question of all. Did Dinopithecus attack our ancestors? Here the fossils become very strict. The current record gives us skulls, teeth, site associations, dietary proxies, and phylogenetic placement. It does not give us a Dinopithecus tooth mark securely identified on a hominin bone, and it does not give us a direct scene of confrontation. The ecological argument that Dinopithecus may have threatened hominins rests on overlap, anatomy, modern baboon analogy, and the demonstrated vulnerability of early Homo and Paranthropus in South African landscapes. That is a serious argument, but it remains an inference. Fossils are good at telling us who shared the landscape and what sort of animals they were. They're often much worse at telling us the exact social history of their encounters. This is why the most responsible language around Dinopithecus is may have threatened rather than certainly hunted. The fossils support the first phrasing. They do not securely prove the second. There is one more thing the fossils tell us very clearly, and it may be the most important lesson of all. They tell us as much about the quality of our knowledge as about the animal itself. The Cradle Review stresses that many faunal reports are decades old, and that more robust reporting and reanalysis are still needed. Modern digital work has begun to change that by scanning and archiving important specimens, including SK554 in the Ditsong archive, which means researchers can revisit morphology with better comparative tools than earlier generations had available. That is encouraging because it means Dinopithecus is not frozen in an old description from the 1930s or 1950s. It is still being reread. The fossils, then, are not just relics. They are active evidence. They continue to say new things when methods improve, but they also continue to remind us that the picture is partial, and that certainty in paleoanthropology is usually earned slowly, specimen by specimen, not declared all at once because the title of the video sounds exciting. So when all of that is put together carefully, the portrait that emerges is strong even without pretending to be complete. The fossils really do tell us that Dinopithecus was a very large early Pleistocene baboon-like primate living in South Africa, one known chiefly from skulls and teeth, closely tied to the papionin story, probably flexible in diet, and present in the same broad ecosystems as hominins and other dangerous mammals. They also tell us that the record is thin enough, the taxonomy difficult enough, and the missing skeleton extensive enough that many of the liveliest details remain beyond direct proof. That combination is not a weakness. It is what good paleontology looks like when it is being honest. We know enough to take Dinopithecus seriously. We do not know enough to turn it into a perfectly illuminated character with motives, habits, and a weekly routine. And that careful middle ground is exactly where the larger meaning of the animal begins to come into focus, because once the fossils have done all they can, the remaining question is what a creature like this says about how uncertain the human future once really was. So after all of that, we can finally come back to the bold claim at the centre of the story and ask what it really means to say that an ancient primate nearly erased our story. The careful answer is that Dinopithecus did not almost wipe out modern humans by itself, and the fossils do not support that kind of dramatic one creature versus humanity version. What they do support is something more grounded and in some ways more unsettling. They show that southern Africa in the Plio-Pleistocene held a monkey fauna far richer than the one there today, with 11 Dinopithecid species known from the period and as many as 6 possibly living at the same time. Some of those monkeys likely shared ecological communities with hominins, and the same review explicitly argues that hominins in the generalist feeder niche could have affected other primates through competition and perhaps predation. If that was true in one direction, then pressure in the other direction is hardly difficult to imagine. In a landscape already full of danger, a very large, socially complex baboon-like primate did not need to become the sole cause of human failure to be historically important. It only needed to be one more serious force acting on lineages that were still fragile enough to break. That fragility is the part modern people often underestimate, mostly because we know how the story ends for us, and tend to read that ending backward into every earlier scene. But the South African record around 2 million years ago does not describe a secure human future. It describes overlap, experimentation, and uncertainty. The Drymalin evidence shows that early Homo, Paranthropus, and Australopithecus overlapped in South Africa around 2 million years ago, which means the hominin picture was plural rather than singular. The same broader time frame also captures a period of faunal turnover and ecological change in the region. In plain language, the human line was not a single confident arrow moving straight towards success. It was a set of primate populations trying to persist, while the environment, the predator guild, and the surrounding mammal community were all in motion. Once you recognise that, the idea that another large primate could matter a great deal stops sounding exaggerated. It starts sounding like exactly the kind of pressure that would count in a world where the margin for survival was already narrow. That narrower margin becomes even clearer when predation enters the picture. The 2024 reassessment of the Swartkrans specimen SK54 argues that the fossil is more likely Homo than Paranthropus, and states plainly that the Swartkrans evidence suggests Homo was prey for leopards. That matters because it undermines the older, easier story in which early Homo stands apart from the rest of the hominins as a more technologically capable, more predator-resistant form already on its way to ecological control. If Homo could still be carried off by a leopard, then no hominin in that landscape was operating under conditions we would reasonably call safe. The human future was not being built from a position of dominance, it was being built from a position of exposure. And when exposure is the baseline, every added source of competition, intimidation, displacement, or opportunistic aggression matters more than it would in a larger, stabler, less vulnerable population. This is why Dinopithecus belongs in the discussion at all. The fossils show that it was a very large and sexually dimorphic fossil baboon species found at Scherverberg and Swartkrans, with a robust and rugged skull, a strong chewing apparatus, a long muzzle, and a broad interorbital region. That description may sound dry on first hearing, but in a papionin it adds up to something very specific. Large size means physical authority. Sexual dimorphism usually points to a social world where competition among males is pronounced. A long muzzle means space for large canines, and in baboons those canines are not ornamental. They are part of rank, threat, and escalation. A strong chewing apparatus points to force and dietary resilience. Dinopithecus, then, was not just another monkey wandering through the background. It was one of the animals most obviously built to hold ground, process difficult foods, and make other bodies think twice before coming too close. At that point, the meaning of nearly erased our story starts to shift into better focus. It is not about one spectacular confrontation. It is about cumulative pressure in a fragile system. A lineage close to the edge does not need to be attacked constantly to be damaged badly. It can be worn down by losses among juveniles, by lower quality feeding opportunities, by repeated displacement from safe routes or good patches, and by the sheer stress of living beside animals stronger than itself. The Southern African Monkey Fauna Review makes this logic explicit in broad ecological terms. It argues that some Plio-Pleistocene monkeys likely lived in the same communities as hominins, that niche partitioning may have helped maintain the unusually high primate diversity, and that hominins in the generalist feeder niche could have altered monkey behaviour and community structure. That is not a romantic picture of coexistence. It is a picture of overlapping primates trying to survive on the same changing ground. In such a setting, Dinopithecus did not need to specialise in killing hominins. It only needed to be one of the more formidable claimants in an already crowded primate world. There is also a demographic side to the story that makes everything harsher than it first appears. Long-lived primates reproduce slowly. Their young take a long time to mature. Their social systems depend on adults surviving, and on juveniles being protected through many risky years. That means small increases in danger can matter enormously. If a primate lineage loses too many infants, too many adolescents, or too many breeding females, it does not bounce back quickly. South African hominin sites and the modern primate comparisons they invite keep forcing the same lesson on us. Medium-sized terrestrial primates live under tight demographic limits, when the record now tells us that at least one Paranthropus robustus individual from Swartkrans was among the smallest known adult hominins in the fossil record, and that even Homo may have fallen prey to leopards, it becomes easier to understand how exposed these populations really were. A lineage like that does not have much room for additional pressure from a giant papionin, already adapted to the same broad setting. Climate change only made that tighter. The recent large mammal review of the cradle concludes that faunal reconstructions across these sites commonly show a trend of wooded landscapes giving way to grasslands. That does not mean every location followed one simple ecological script, but it does mean the world of these cave faunas was becoming more open in repeated and significant ways. In practical terms, more openness alters cover, route choice, predator visibility, water access, and the balance between refuge and exposure. A large terrestrial papionin may cope with some of that very well, especially if it is flexible in diet and socially cohesive. A small hominin group carrying infants and trying to manage predators, tools, and daily foraging under the same conditions has a harder time. The move toward more open environments therefore did not merely change the scenery, it sharpened competition and made mistakes more expensive. In that sort of world, an already imposing primate neighbour becomes more dangerous without needing to evolve any new behaviour at all. Dinopithecus itself seems to have been flexible enough to matter under those changing conditions for a time. Isotopic and dental work from the literature cited across recent reviews indicates that it was not narrowly confined to one feeding niche, and the older monkey fauna synthesis frames the broader southern African primate community as one in which niche partitioning and ecological overlap both mattered. A big, broad-feeding primate is often a difficult competitor because it can exploit more than one habitat type and more than one class of resource. That does not mean it wins forever. Dinopithecus eventually vanished, and the southern African monkey fauna was dramatically reduced from its earlier diversity. But disappearance in the end does not make an animal unimportant in the meantime. On the contrary, extinct species can shape the pathways of other lineages precisely because they are present during the vulnerable phases and absent only later after the sorting is done. Dinopithecus seems to have been one of those shaping presences. It did not survive to the modern world, but while it was there, it belonged to the set of forces any small hominin population had to reckon with seriously. And yet this is also where the fossils force discipline on the story. They do not let us say more than they can support. The 2017 study of South African fossil monkey cranial variation warns that many cranial measurements fail to distinguish fossil papionin species, and even genera as cleanly as they do living ones, and the authors conclude that some extinct taxa may not be separable on craniofacial measurements alone, or that current taxonomic designations are confounded. They also point out that Dinopithecus and some of the other large fossil papionin genera are represented by limited and often distorted material. That means there is a hard stop beyond which narration becomes guesswork. We cannot honestly say we know its troop size, the exact nature of its displays, its day range, or its specific interactions with hominins. The most interesting thing the fossils tell us here is not that certainty is impossible, but that caution is part of the evidence. Dinopithecus becomes more impressive, not less, when it remains an ecological reality rather than a fully invented character. Still, uncertainty cuts both ways. It prevents overstatement, but it also keeps us from underestimating what a creature like this may have meant on the ground. When fossils are sparse, the safest strategy is not to pretend the animal did nothing unusual. It is to combine the secure facts we do have. Dinopithecus was very large. It was a papionin, and thus part of a clade whose living members are intelligent, social, adaptable, and capable of serious aggression. It had a skull built for force and display. It lived in early Pleistocene South Africa, in the same broad hominin-bearing environments as species that were demonstrably vulnerable to predators. It belonged to a primate community more diverse, and in some respects more imposing, than the one in southern Africa today. Even without a single direct fossil proving a Dinopithecus hominin clash, that combination is enough to make one conclusion feel entirely reasonable. Our ancestors were living in a world where another primate could absolutely have been one of the things making their success less likely. That is why "nearly erased our story" is best heard as an evolutionary statement rather than a tabloid one. Humanity's story was not almost erased because Dinopithecus stood alone against it. It was almost erased because the line leading eventually to us was once only one vulnerable branch among several, and that branch existed in landscapes crowded with forces stronger, faster, larger, or better established than itself. Some of those forces were carnivores, some were climate and habitat turnover, some were competing hominin lineages, some were other primates. Dinopithecus matters because it brings that last category into focus. It reminds us that our ancestors were not just shaped by cats, drought, and stone. They were also shaped by neighbours not entirely unlike themselves, only bigger, more heavily armed in the face, and perhaps better suited to hold contested ground during a difficult stretch of time. If the human line had broken under those combined pressures, there would be no final winner standing in the fossil record to explain what almost happened. There would simply be another vanished primate experiment. There is something else worth keeping from this story, and it has less to do with Dinopithecus specifically than with how we think about human origins. We tend to narrate the past as if our arrival made everything before us look provisional. But the deeper lesson of the South African caves is the opposite. For a very long time, we were the provisional ones. The world did not know and did not care that one hominin lineage would eventually write papers, build museums, and worry about whether extinct baboons were underrated. Dinopithecus did not need to understand our future to threaten it. It only needed to live effectively in its own present. That is perhaps the most sobering part of the whole subject. History, at its deepest level, is not protected by importance. It is protected only by survival, and survival is never automatic while it is still being negotiated. So when we step back and look at the whole picture, the claim turns out to be defensible in a careful sense. Dinopithecus was not the almost killer of humanity in the way a dramatic title might first suggest, but it was part of a world harsh enough, crowded enough, and dangerous enough that our story could have ended before it ever became what we now call human history. A giant primate like this mattered because it belonged to the set of ordinary pressures that can quietly erase fragile lineages, not with one decisive blow, but with enough intimidation, enough competition, enough overlap, and enough added risk to make survival harder than it already was. The fossils do not let us turn that into a legend. They do let us recognise it as a possibility worth taking seriously. And once you do take it seriously, the past becomes a little less comforting and a lot more real, because suddenly the human story no longer looks inevitable at all. It looks like something that very nearly never got the chance to continue.